video, I'm going to be talking about the naive Bayes algorithm. So naive Bayes classifiers are a family of simple probabilistic classifiers based on applying Bayes theorem, and we will assume strong assumptions between the features. So let's take a look at the Bayes theorem. So as we can see here, using the Bayes theorem, we can find the probability. As you can see here, we have the conditional, this is the conditional probability formula. So conditional probability goes like this. Using Bayes theorem, we can find the probability of A happen, given that B has already occurred. B is the evidence and A is the hypothesis. We make the assumptions that the features are independent. That is, the presence of one particular feature does not affect the other. So when we are using the naive Bayes algorithm, let's say we are trying to predict the outcome between two features. So the naive Bayes algorithm assumes that these two features are independent. They are not the same. So that means that if a change occurs to one particular feature, that doesn't affect the other feature. But in reality, we know that these features may have a relationship. But when we are using naive Bayes algorithm, we simply assume that there is independence between the features. So as you can see, using the naive Bayes formula, we have the posterior probability, we have the likelihood, we have the class prior probability, and then we have the predictor prior probability. So the prior probability describes the degree to which we believe the model accurately describes reality based on all of our prior information. And then the likelihood describes how well the model predicts our data. And then we have the predictor prior probability, or the normalizing constant, the constant that makes the posterior paper density integrate to 1. So let's say we are trying to predict, let's say, if an email is a spam or not. So when we use the naive Bayes classifier, it will predict that the email, maybe it predicts that the email is a spam, let's say by 0.80, and then not spam 0.20. So if we add those probabilities, they should all add up to 1. So that's the job of the normalizing constant. And then we have the posterior probability, which represents the degree to which you believe a given model accurately predicts the situation given the available data and all of our prior information. So let's take a look at this data. So let's say we want to play golf, and then the data we are given here determines if we are going to play golf or not. So as you can see, that golf is not suitable for us to play golf when it is rainy, hot, the humidity is high, and the wind is there is no wind. And then it's suitable to play golf if it is overcast, hot, high, false, and yes. So remember, when I first started the video, I talked about that the naive Bayes algorithm assumes that the features are independent. So this means that if the outlook is overcast, that doesn't mean that the temperature will be hot. No, the outlook can be overcast, but the temperature can be low. So there is no independence between the features when we are talking about the naive Bayes algorithm. But in reality, we know that there must be a relationship between these features. So you can see it is also suitable to play golf when it is sunny, the temperature is cool, the humidity is normal, and then there is no wind. So as you can see, so if we take this data and then we try to predict the outcome to play golf or not, so the naive Bayes algorithm will treat each one of these features as independent, and then we'll predict the outcome. So we make two assumptions here. One is stated above. We consider that these predictors are independent. That was what I was talking about. So that means that if the temperature is hot, it does not necessarily mean that the humidity is high. Another assumption made here is that all predictors have an equal effect on the outcome. So what this statement really means is that each of these each each of these features have an equal effect on the outcome. So let's say that time we had 4 features. So let's say each and every feature is 0.25 effect on the outcome. If we add all of these 0.25, it will give us 1, which is the outcome. That is, the day being windy does not have more importance in deciding to play golf or not. So as you can see that one feature cannot determine our outcome, but all of the features have equal effect. So if that means that the outcome is overcast, that doesn't mean that we cannot play golf, but we need to use all the features to determine the outcome. So the variable y is the class variable that is to play golf, which represent if it is suitable to play golf or not given the condition. And then the variable x represents the parameter or features. So as you can see here, the variable y in our formula are the classes. In our case, it's 1 when when we when it's 1 when you play golf, and it's 0 when you cannot play golf. And then x are the features. So our features, remember, x represents outcast, temperature, humidity, and then wind. So these are the features. So this is another formula of the naive Bayes classifier. So here x, we can replace x with outcast, humidity, temperature, and then windy or not. So here we can say x1, we can represent our x1, which is, let's say, the first row, and then the class. And then if you can still remember, in our first row, if we take this first row, here we cannot play golf. So x will be the features outcast, and then the class will be 0. And then the next row, it will be outlook, and then again the class is 0. And then here we take all these features x, and then y will be 1 since we can play golf. So what are the pros of using the naive Bayes? So it is easy and fast to predict a class of test data set. So the other thing is naive Bayes classifier performs better compared to other models when we assume that there is independence between the features. And the other thing is that it performs well in the case of categorical input variables compared to numerical variables. So what are categorical input variables? So categorical input variables are variables that represent a category. Let's say we say 1 will represent if it is overcast, and then 0 will represent if it is sun. So these are variables that represent categories. The cons of naive Bayes is that the independent predictor assumption. So since the naive Bayes assumes that there is independence between the features, but we know that in reality there is a relationship between the features. So let's say if it's overcast, then the temperature might be cool. So in reality, there is some relationship between the features, of which in naive Bayes to predict that there is independent. And then use of the naive Bayes. So naive Bayes is used for real-time systems, for example, like credit card fraud prediction. And then we can also use the naive Bayes for multi-class prediction. And then it can also be used for recommendation systems. For, let's say, for example, if you go on Spotify and then you play a certain genre of music, and then the next time you open Spotify again, it will recommend another same song in the genre. So you can see that that's one application of the naive Bayes algorithm. So thank you for watching, guys. In the next video, I'll be demonstrating how to use the naive Bayes using programmatical. Demonstrating how to use naive Bayes programmatically. Thank you for watching, guys. Please subscribe and click on the notification bell so you can receive more videos like this every week. Thanks for watching. using the Scikit-Learn library. So here I imported the NumPy library, which is used for mathematical operation, and then pandas, which we are going to use for data pre-processing, and then model selection, which we are going to use to split our data set into training and test set. And then here I've created this variable to store the CSV file, the tennis CSV file, which I have in my PC. And then here I read the CSV file, and then I stored it into the data variable. So visualize the information in our data set. We are going to use the data and then the info method from the pandas library. And then, as you can see, in my data set, I have 14 rows, and then I have a total of 5 columns. I have the outlook, the temperature, humidity, wind, and then play. Play is going to represent classes. One which is going to represent if one is going to play tennis based on these features. So if you remember from my previous video, I said that naive Bayes assumes that there is independence between the features. That means that the presence of one feature doesn't affect the presence of the other feature. That means that if the temperature is high, it doesn't mean that the humidity is high, and if it is windy, it doesn't mean that the temperature is high. The next thing is we are going to display the columns. To do so, just use dot columns. And then the next thing is we are going to display the first 5 items in our dataset. To do so, we use the dot head method, and then we pass in 5 as the argument, as you can see. If you want, you can display the last five items in our dataset. And to do so, you use the data.tail method, and then you pass in 5 as the argument. As you can see here, we have 1, 2, 3, 4, 5 rows. And then the next thing is we are going to define our X features. To do so, we use the dummies method from the pandas library. So this creates dummy variables. So if you guys are not familiar with what are dummy variables, I'm going to put a link in the description below that is going to explain what are dummy variables. So here we're going to specify the columns. And then the next thing is we are going to define our labels. And then to do so, we use the data frame method. We use the data frame instance. And then we specify the column we want. Okay, sorry guys, this should be PD. And then we can print the information. And then the next thing is we are going to split our data set into training and test set. To do so, we import the model selection, the model selection instance from scikit-learn, and then we import train test split from model selection. So we pass in our features, our labels. Then we are going to divide our data into 20% training set and then 80% training set. So the next thing is we are now going to use the Gaussian naive Bayes from the scikit-learn library to make predictions. So to do so, we need to import the naive Bayes from scikit-learn library. So in this tutorial, I'm going to use the Gaussian naive Bayes. We are going to create an instance of the Gaussian naive Bayes. The next thing is we are going to fit our training set into our model. So to do so, use the .fit method from the scikit-learn library. The next thing is we are going to make predictions. So to do so, we use the dot predict method from the scikit-learn library. Then we are going to print. We're going to print the predictions. Oh, I'm sorry. So as you can see that if we provide these values, it's going to predict that we are going to play golf. And then the next thing is we want to evaluate how our model is performing. So we use the dot score method from the scikit-learn library, and then we pass in the test set. So here we pass in the test set because our model was trained on the training data set. So we pass in the test set because we need to evaluate our model on variables or values which the model has not seen. And then we are going to print the score. As you can see that our model is an accuracy of 33%. The reason being is that I have 14 columns. So 14 columns, the data is not enough for our model to generalize well. So one thing to do if we want to increase the accuracy of our model is we need more data, and to solve this is we need to add more rows into our data set. As you can see, I have only 14 rows in our data set, and the model is having a difficulty in generalizing. So the solution here is to find more training data and then train our model, and then if you increase more training data, you can see that the accuracy of our model can improve. Thank you for watching, guys. I hope this video helps you a lot. And then the best thing you can do is you can try the Gaussian naive Bayes on different data sets, which you can find on Kaggle. Thanks for watching. Hello guys, welcome to my video. In this video, I'll be talking about the support vector machine. So the support vector machine is a discriminative classifier formally defined by separating hyperplane. So let's say if it's a two-dimensional, if we have a two-dimensional space, let's say if we have an x and y axis, in this case, the hyperplane is a line dividing a plane into two parts, and then where each class lay in either side. So let's say in this case we have the y-axis, and then we have the x-axis, and then we have two classes. We have plotted two classes on the graph. We have the blue class represented by the blue dots, and we have the black class represented by the black dots. So in this case, how do we separate these classes, and how do we discriminate each of these classes? So what the support vector machine does is, support vector machine uses a hyperplane to separate the two classes. So how does the hyperplane separate the two classes? So the hyperplane should separate these classes fairly. So which means that the hyperplane must pass something like this. Okay, I'm sorry. I'm sorry. The line should be equidistant. Okay, let me use the ruler. So it's something like this. So as you can see, this is our hyperplane, and this hyperplane separates our two classes. So this means that if a class falls under this hyperplane, it belongs to the blue class, and if and if a and then if something falls above this hyperplane, this means that 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 item belongs to the black class. And then we have a second scenario in which our data set we have a second scenario in which our data set lies in both the x and y axis. So in this case, how do we demarcate the demarcate the two classes? Uh, so here, the best thing we can do is to apply transformation. So I hope you guys are familiar with geometry. So the best way is to apply transformation. Let's say if we transform this blue dot here, it will end up being here. And then if we take this, it will end up being here. And then if we take this black dot, it will end up here. And then if we take this, it will end up somewhere here. And this will end up somewhere here. And then this will end up here. So and then let's erase these black dots so that there will be no confusion. Okay, I'm sorry. I've 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 deleted the line. So and then the next thing is we need to also apply transformation to these blue dots. Then if we take this, let's say we'll just estimate that it will end up being here. This one will end up being here. This will end up being here. And then this will end up being here. Then this will end up being here. And then this blue dot will end up here. And this one will also end up here. And this will end up here. And then so we can erase these blue dots to avoid confusion. So as you can see, now it is easier for us to separate these two classes, since what we can simply do is simply we can simply draw a hyperplane separating these two classes. As you can see, we have created a hyperplane which separates these two classes. Okay, guys, I'm sorry, I've deleted the X. So let's say this is the X axis. So as you can see, we have created a hyperplane which demarcates between these two classes. So which means that if anything lies above this, it will belong to the blue class. If anything lies below this, it will belong to the black class. And then let's take a look at another scenario where we have outliers. So in this scenario, you can see that the blue class overlaps with the black class. So in this case, how do we demarcate these two classes? So to demarcate these two classes, there are two methods. The first one is we can try to ignore we can try to tolerate the outliers, and the second one will be we do not tolerate the outliers. So let's say if we tolerate the outliers, we can draw a hyperplane which separates these two classes, and the hyperplane will be something like this. And let's then draw the hyperplane. So as you can see, so as you can see, guys, this hyperplane tolerates the outliers. So as you can see that we have these two black dots which belong to the black class, but they are simply outliers since they belong to this to this blue class. And then the other thing will be to apply zero tolerance to the outliers. So let's draw another hyperplane. So here we can simply try to we can draw something like this as a hyperplane. So as you can see that this our hyperplane does not tolerate a zero tolerance to outliers. So here we try by all means to separate the two classes. But as we can see, as you know, in machine learning, we'll be dealing with millions of training data examples. So it is very difficult for us to have zero tolerance if we have millions of examples in our dataset. So in the next video, I'll be talking about the hyperparameters of the support vector machines. So we'll be trying to visualize the hyperparameters using we'll be trying to visualize the hyperparameters of the support vector machines. So thanks for watching, guys. Uh, if you need more videos like this, please subscribe to my channel as I release these videos each and every week. Thanks for watching, guys. Thank you very much. Video. In this video, I'll be showing you how to use decision trees to predict house prices. So a decision tree is a flowchart-like structure in which each internal node represents a test on an attribute. For example, when we flip a coin, if it's going to be a head or a tail, each branch represents the outcome of a test, and each leaf represents a class label. For example, here this this leaf node represents a class class of bedrooms. This represents class of lot size classes. So one thing is we have a root node. The first leaf, this one is the root node. This node. So the root node represents an entire population or a sample, which is then further divided into other homogeneous sets. So we have a decision node. Let's say if we have a root node, and then these are decision nodes. So when a subnode splits into further subnodes, then it is called a decision node. So when this splits into subnodes, it is called a decision node. And then we have the terminal leaf. So a terminal leaf is a node that does not split. So as you can see here, let's say we want to predict the price of houses based on the bedroom class. So we first ask ourselves a question: does the house have more than two bedrooms? If it's yes, we ask ourselves another question based on the lot size class. Is the lot size larger than 11,500 square feet? If yes, then the price will be 233 US dollars. If no, then the price will be 170,000 US dollars, which is logical because if it's less than 11,500, it cannot be like it, the price cannot be greater than when it is more than 11,500. And then on the other side, we ask ourselves, does a house have two bedrooms? If it's no, then we ask ourselves another question based on the lot size class. Is the lot size larger than 8,500 square feet? If it's yes, then the predicted price will be $188,000. If no, then the predicted price will be 146,000. The other thing is decision trees can also be used, like for example, like banks can also use decision trees to predict if it's good, if it's a good investment for them to give a loan to their clients based on their savings. For example, let's say we have the root node, and the root node represents savings, whether they are low, medium, or high. If the savings are high, we ask ourselves another question based on the income class. Is the income of our client less than or equal to $30,000? If yes, then it's a bad risk. We cannot give him a loan. If no, then which means that the income may be greater than 30,000, which is a good risk. And then here you can see that if our client savings are medium, then it's a good credit risk. And then here, if the savings of our client are low, we ask ourselves another question based on their assets. Are their assets low? If yes, then it's a bad risk. We cannot issue them a loan. If it's no, it means that their assets are high. It's a good risk, so we can give them a loan. So these are some of the common terms used with decision trees. So I have put a link in the description, which a link in the description of this Jupyter notebook. So if you can want, you can go on GitHub, you can download the Jupyter notebook, and then you can play around with the decision trees. You can read what decision trees are and some of the things that I may have left. So what are the advantages and disadvantages of decision trees? The advantages are that decision trees are easy to understand and it's easy to generate rules using decision trees. The other thing is that decision trees may suffer from overfitting. For example, when we are dealing with real world data sets, a decision tree can be very, very large and can get very, very complicated, which can lead to overfitting. So overfitting is a scenario whereby our model is is a scenario whereby our model does not generalize well. So our model is good is good at predicting something when it's given values that are similar to the training set. But when we give it like other to predict on other values that our model have not seen or on the data set in which our model have not seen, the model will have difficulties in making predictions. So the other disadvantage is that decision trees do not easily handle numeric data. And the other thing is decision trees can be quite large and pruning is necessary. So here I'll be using a decision tree regressor. So what is regression? So regression is a statistical measurement used in finance, investing, and other disciplines that attempt to determine the strength of the relationship between one dependent variable, usually denoted by y. In our case, the variable y are prices and other changing variables, which in our case, the variables are going to be bedrooms, land size, and so forth. So we want to determine the relationship between the bedrooms and the price of the house, like latitude and the price of the house. So here I have imported NumPy, which is a mathematical library, and then pandas, which we are going to use for preprocessing our dataset. So this is the file path to my file which contains the dataset, and then here I'm going to read the dataset into pandas, and then I'm going to store it, and then I'm going to store it in the variable df. So let's run our code. And then we want to get a description of our dataset. To do that, we use the describe method from the pandas library. And then if we want to display our columns, we can just use the dot columns from the pandas library, and then this would will display columns in our data set. For example, we have the suburb, address, rooms, type, price, method, seller G, date, distance, postcode, bedroom, bathroom, car, lane size, building area, year built, council area, latitude, longitude, engine name, property count, and so forth. And then the other thing is we want to drop now empty values. So here we specify the x is equal to 0. So when the x is equal to 0, we'll be talking about among the along the y-axis. And then the other thing is we want to here we want to create our target variable, which we will be predicting using our model. So our target variable in this case is going to be price. So we just say y is equal to df, and then we specify the column of the target variable, which is price. And then we want to predict the target variable price based on the features rooms, bathroom, lane size, latitude, and longitude. So we pass in we create the variable x, and then we pass in our features here into our data frame. And then we want to get a description of our features. So these are this is the description: rooms, bathroom, lane size, latitude, and longitude. Third thing is we want to display the first few items in our data set. To do that, we use the head method from the pandas library. And then if we want to also display the last few items in our data set, we use the tail method from the Scikit-Learn library, from the pandas libraries, I'm sorry. So the other thing is we are going to use our decision tree regressor. We can just do it in a few lines of code thanks to the Scikit-Learn library. So here we from scikit-learn.tree import the decision tree regressor, and then we create the instance of the decision tree regressor, and then we pass in our training set, which is x, and then we pass in our labels, which is y, as you can see, and then we want to make predictions. So as you can see, these are the predictions. These are the price predictions. And then the other thing I want to talk about is the mean absolute error. So the mean absolute error measures the average magnitude of the errors in a set of predictions without considering their direction. It's the average over the test sample of the absolute differences between prediction and actual observation. So let's say we have this y is our target, this y is our label. For example, the y that we derived from our data set, this is the y. And then this y head is the predicted value of y. So we want to get the difference between our target value y and the predicted prices. So to do that, we can do that, and then we can divide it by the total number of samples in our data set. So that's what the mean absolute error is. So as you can see here, we can also import the mean absolute error from the scikit-learn.metrics, and then we can then make predictions. As you can see, our mean absolute error here is very, very small. It's about 1,115 $1,115. But there's something wrong. We used our X value from our training set to make predictions. So as you can see that our model obviously is going to be very, very good because it has already seen the data set in the training set. So what do we need to do? So to make predictions, we need to create a test set. We need to create a test set and then test our model on the test set data which the model has not seen, so that we can evaluate if our model is performing well or not. For example, let's say you are given a math example, and then the next day is the math example comes in a test. The, the chances are going to be you are going to totalize that math test. But if the math test comes with 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 different questions, but from the examples that you learn, chances are that they are going to test if you are generalizing well or not. So to do that, we need to split our dataset into training and test set. So to do that, we import the train test split from the from the Scikit-Learn library, and then we then use 20% of our data set as the test set, as you can see 0.2. So it's 20% of our data is this test set. Then we can then create the decision tree regressor instance class, and then we can fit our X train value and our Y train values, and then we can make predictions based on our test set, which is the val X. And then, as you can see, the mean absolute error is around $277,370. And then our score is around 51%, which is very, very low. So in the next video, I'm going to be showing you how to optimize your decision tree. So thanks for watching, guys. You may click the subscribe button and the notification bell so that you do not miss any of my videos. I'll be releasing soon. Thanks for watching. I'll be explaining how to fine-tune your decision tree by tweaking the decision tree hyperparameters. So the first hyperparameter we're going to talk about is the minimum sample split. So the minimum sample split represents the minimum number of samples required to split an internal node. So this can vary between considering at least one sample at each node to considering all the samples at each node. So when we increase this parameter, the tree becomes more constrained as it is to consider more samples at each node. So I'm going to illustrate how the mean samples split hyperparameter works. So let's say we have our decision tree, and then we split this decision tree. Sorry. Let's say we split this decision tree, something like this. Then split it in something like this, like this. So let's say here we have 100 observations, and then let's say here 60 observations, and then here we have 40 observations, and then let's say here we have 20 observations, and then let's say like here, let's say like here we have like 10 observations. Then let's just assume that here we have 5 observations. Then let's say here we have 1 observation, and then we have 2 observations. So what the minimum sample split does is that it determines how further can we split our decision tree. So the minimum number of samples that we can only split is 2. So we cannot split 1 sample. So this is wrong. So the minimum number for the mean sample split is equal to 2. So we cannot go below at this number. If you try it with the Scikit-Learn library, it will give you an error. So always keep this in mind. So the next hyperparameter I will talk about is the max depth. So the max depth indicates how deep our tree can be. So the shallower our tree is, that means that our tree cannot capture more information. But the deeper our tree is, the more our tree captures more information. But this can also lead to overfitting, as our model can get complicated. So that's where we can apply pruning to reduce the size of our decision tree. So here I've created the mean accuracy error to evaluate different values of our max depth. So here our function takes in the max depth, and then takes in our training example, and then takes in our test example, and then the y value for the training set, and then the y value for the test set. And then we can then create our model, which is a decision tree regressor. Then specify the max depth equal to the max depth, and then random state, we set it is equal to 1, and then we then fit our train and test set, and then we make our predictions, and then we then use the mean absolute error to evaluate the mean absolute error, and then we then create an array with different values of the max depth. So we have 5, 10, 20, 30, and then 60. So our tree can have up to five leaf nodes, 10, 20, 30, up to 60. And then we then loop through our values in our array, and then we then display different mean absolute errors for different values of the max depth. So as you can see here, the best value for our max depth is 10. As you can see, it has the lowest minimum, it has the lowest mean absolute error. And then we go on to the mean sample split. So as I have illustrated the mean sample split, so the mean sample split represents the minimum number of samples required to split an internal node. So here I've done the same. Instead of taking our max depth, our method will be taking the mean sample split, our training set, our x value for the training set, and then our x value for the test set, our y value for the training set, and then our y value for the test set. And then we then create our model, our decision tree regressor model, and then we then specify the mean sample split. And then the next thing is we then create an array with different values of our mean sample split. As I have specified, the minimum number of the mean sample split, you can only split up to 2 observations. We cannot go below that. So keep that in mind, 2 observations. So the idea behind optimizing your decision tree is you need to try different values of the max depth and then different values of the mean sample split. There is no certain value. So it's an experimental process. Try different values until you get values which until you get values where your model is a better accuracy. So as you can see here, the best oh sorry, this should be mean sample split. So the best value for our mean sample split is 30, as you can see, is the value with the lowest mean absolute error. And then our next hyperparameter is the mean samples leaf. So the mean samples leaf is the minimum number of samples required to be at a leaf node. This parameter is somehow similar to the mean samples leaf. However, it describes the minimum number of samples at the leaf and at the base of the tree. So at the terminal node, this describes the minimum number of samples at the base of the tree. So this is the base of the tree. So the mean samples leaf determines the minimum number of samples at the base of the tree. So this is the base of the tree. So and then the mean samples leaf. So it determines the minimum number of samples at the base of the tree. Yeah, the base of the tree. So in this mean absolute error method, I've changed our method to take the mean samples leaf, and then we then loop through different values of the mean samples leaf, and then you can see that a mean samples sorry, this should be mean samples leaf. As you can see that 10 is our best value as it is the lowest mean absolute error. And then we can then combine these hyperparameters. So in this, I've imported the decision tree regressor from the Scikit-Learn library. And then I have specified the criterion to be the mean square error, and then splitter to be best. So the splitter, best splitter, this means that our model will be only considering the best. We'll try by all means to split our data the best way possible. And then I have specified the mean samples, the means the mean samples leaf to be 3. And then I have specified the max depth to be 50. And then I have specified the mean samples leaf to be 7. And then we get an accuracy of 61% as compared to our previous accuracy in the previous video, where we got an accuracy of 52%. So that's a slight improvement. So the other thing is when you are searching for the best hyperparameters, we can use the random search from the Scikit-Learn library. So to use the random search, we first create a dictionary with the different hyperparameters. So here we specify the max depth, and then we generate random numbers from 1 up to 100. So we generate random numbers from 1 up to 100. So our decision tree can vary from 1 up to 100. And then we then specify the mean sample split from 2 up to 40. As I specified that the minimum number of the mean sample split is 2, as we cannot split one example. So this ranges from 2 up to 40. And then we specify the mean samples leaf. And then we specify the number, and then this number should range from 1 up to 50. And then we then instantiate our decision tree, and then we then pass in our decision tree into the random search, and then we pass in our parameter dictionary, and then we specify CV to be 5, and then we then fit our training example, the X value for our training example and the Y value for our training. And then what random search will do is it will look for the best parameters for the best parameters in the dictionary, in this dictionary that we have specified above. So here the max depth will be here our tuned tree parameters and our best hyperparameters will be a max depth of 52, a minimum samples leaf of 10, a minimum sample split of 6, and the best score, as you can see that our best score is 69%. Is 69% accuracy, which has improved from our previous score, which was 61%. So thank you for watching, guys. So in the next video, I'll try to talk about the entropy. I'll try to talk about the entropy, and then how you can also use the entropy to improve your decision tree classifier. As in the previous two videos, we've been talking about the decision tree regressor. In the next video, we'll be talking about the decision tree classifier. Thanks for watching. Hello guys, welcome to my video. In this video, I'll be talking about the boosting technique and other boost in particular. So in my last video about random forest, I talked about the bagging technique. So unlike bagging, where a random sample of the training run of the unlike bagging, where a random sample of the training set is given to a base classifier, in boosting we create base learners sequentially, and each base learner learns from the mistakes made by the other base learner. So let's say, for example, we have a data set with 5 records. So let's say, for example, we have a data set with 5 examples. So, and let's say we feed these examples into a classifier. And then let's say this classifier misclassifies 2 records. So let's say it misclassified these 2 records. So these misclassified 2 records are then fed into another classifier, which then makes predictions. Let's say this classifier again misclassified these 2 records. So we then take these 2 records and then feed them into the other classifier. So that's basically how bagging works. So each classifier learns from the mistakes. Each weak classifier learns from the mistakes made by the other classifier. So now let's move on to other boost. So what AdaBoost does is that it combines a set of weak classifiers. So what do I say when I say a set of weak classifiers? So in AdaBoost, we use what we call stumps. So a stump is just a decision tree with two leaf nodes. A decision with just two leaf nodes. So this is what we call a stump. So we use a collection of stumps to make decisions. So let's take a look at this data set and let me try to explain AdaBoost. So let's say we have three features. We have x1, we have x2, and then we have x3. And then we have, let's say, the output, which is going to be a binary output. And then let's say here we have the sample weight. So let's say we have the sample weight. Let's just draw border lines. So what AdaBoost does is that at the first iteration, each record in our features, they have the same weight. So let's say we have 5 records. We have 5 records. Let's say here it will be yes, no, yes, no, and then yes. So here the weight will be 1 over 5, 1 over 5, 1 over 5, 1 over 5, 1 over 5. So all the total number of the sample weight should add up to 1. So if we add up this sample weight, they should always add up to 1. So what we do is, let's say we have a collection of stamps. Let's say this is the first stamp, and then this is the second stamp, and this is the third stamp, which we are going to call x3. So how do we determine which of these following stamps is going to be our base learner? So what we do is we use what we call the entropy. So the entropy is the amount of impurity in a data sample. So let's say here the entropy for the first stamp is going to be 0.24. This one is going to be 0.30. This one is going to be 0.40. So we choose the stamp. We use the stamp with the lowest entropy to be the first base learner for our sequential for all the sequential stamps that we create in AdaBoost. So we said that we create these stamps sequentially so that the mistakes made by the first stamp are going to be fed into the second stamp, and then the second stamp is going to learn from the mistakes made by the first stamp. So that's how AdaBoost works. So in this case, we are going to choose the first stamp, which is based on the feature x1, which is based on the feature x1. So let's say this stamp. Let's say this stamp on the first iteration, these stamps made 4 correct classifications, but one incorrect classification. So what we do before we feed the mistake made by the first stamp into the second stamp, the first thing we need to do is to update these sample weights. So how do we update the sample weights? So the first thing we need to do is we need to calculate the total error. So the total error is the total number of weights, is the total number of sample weight for the incorrectly classified samples. So in this case, our incorrectly classified sample was 1. So the total error is 1 over 5. So keep that in mind. The total error is 1 over 5. The next thing we need to do is to calculate the performance of this stamp, of this first stamp. So we use a certain formula, which I'm going to say, which I'm going to call the performance. Which I'm going to call the performance of stamp is equal to half ln 1 minus the total error divided by the total error. So in this case, it's going to be half ln 1 minus, that was 1 over 5 divided by 1 over 5, which is going to be, so let me calculate the value. So this value is going to be 0.9. Sorry. This value is going to be 0.693. 0.693. So this is the value for the performance of our stamp. So you guys might be wondering, why do we need to calculate the performance of this stamp? So this value is important when we want to update the weights. So to update the weights for the incorrectly classified points, we use another formula, which I'm going to write down. So this formula is the new sample weight. The new sample weight is equal to the previous weight times e to the power of the performance of stamp that we calculated in the previous stage. So this is the formula. This is the formula. So let me just get rid of this decision tree. So here we just create another column. We call it new sample weight. New sample weight. So for incorrectly classified sample, the sample weight for incorrectly classified sample is going to be, remember that we had one incorrectly classified sample. It's going to be 1 over 5 e to the power of 0.693. So let's say, so let's just assume that this was the incorrectly classified point. Yeah. So now what we can do is just calculate the new sample weight. So it's going to be 0.693 times 1 over 5. So our new sample weight here is going to be 0.399. So that's our new sample weight. But I said that we had 4 correctly classified points and 1 incorrectly classified point. So what we do to calculate the weights for the correctly classified points is we just modify our formula. Instead of e to the power of the performance of the stamp, we just introduce a negative value. So here the new weight the new weight for our correctly classified points is going to be 1 over 5 times e to the power negative 0.693. So here it's going to be 0.10, 0.10, and then 0.10, and then again here it's going to be 0.10. Sorry here guys, it's supposed to be 1 over 5. But the problem is that if we add, the problem is that so the problem is that, remember that I said that these sample weights should always add up to 1. But if you add up our sample weights, you will see that they do not add up to 1. So the total is going to be, so the total here is going to be 0.799. So this should be add up to 1. So what we need to do is we need to normalize the sample weights. So we just create another column and then just say normalized sample weight. So normalized sample weight. So what we do here, we divide each of these numbers by 0.799. So if we divide 0.399 by 0.799, we get 0.499, which is approximately 0.5. And then if we divide 0.10 by 0.799, we get 0.1125, which is approximately 0.13, 0.13, 0.13, then 0.13. So if you add up these weights, approximately they'll add up to 1, or it will be maybe 0.9, but now they add up to 1. So I want you to take notice of one thing. So remember that I said this is the incorrectly classified points. And if you check out here, when we updated our sample weights, the weight for the incorrectly classified points has increased, as you can see, from 1.5 to 0.5. So this means, so when this weight is increased, this means that the next the next the next classifier is going to put more emphasis on this incorrectly classified point. So it's going to put more emphasis. So that's how other boost work. So when we first start, we start with equal weights, but when the classifier makes a mistake, we update the weights so that we increase the weights for the incorrectly classified points, so that the next classifier will put more emphasis on the incorrectly classified points, so that it learns from the mistake made by the other classifier. So that's how other boost works. So thank you guys for watching this video. I hope this video is useful and you find the video useful. Please subscribe to my channel and also share so that you can help me to reach more people. Thanks for watching, guys. Cheers. Video. In this video, I'm going to explain AdaBoost mathematically. So if you've not watched my other previous video about AdaBoost, I advise you to do so so that you can understand this video. So AdaBoost focuses on classification problems and aims to convert a set of weak classifiers into strong ones. So the equation for the classification can be represented as f of x. So f of x is equal to the summation from m is equals to 1 up to m. So theta m of x, and then f. So you find that this can be represented as in other research papers or in other literature, they can represent of each as hm of x. So here fm, so fm of x stands for is the mth weak classifier. Is the mth weak classifier. And then here theta m of x represents the corresponding weight. So it's the corresponding weight. So let's say if we have a data set, so let's say if given a data set containing n points, let's say we have a data set with n points. So this is our data set with n points where xi is an element of, and then y so here -1 denotes the negative class while 1 represents the positive class. So the first step is we initialize the weights. We initialize the weight for each data set. We initialize the weight for each data set as w x I y I is equals to 1 over n, where I ranges from I is equals to 1 up to n. So in this case, let's say we have 5 data points. So in this case, if we have 5 data points, then our weight for each data point is 1 over 5. So and then the total sum of these weights should always add up to 1. So the total sum of these weights should always add up to 1. No matter what, they should always add up to 1. So now the next step is so yeah, the next step is, let's say, for iterations from m is equals to 1 up to m, we feed weak classifiers to the dataset and select the one with the lowest weighted classification error. So the first stage is we feed weak classifiers. This is the weak classifier. So we feed weak classifiers and then we select the one with the lowest weighted error. And then the next stage is we need to calculate the weight for the mth weak classifier. That's the next stage. So to calculate the weight for the mth weak classifier, theta m is equals to half, that will be ln 1 minus the classification error over so this guys, if you relate to the previous video, this e of m just represents the total error. So this is just the total error. If you relate from our previous video, this represents the total error. So let's say we had 5 data points, then our classifier makes 2 mistakes. So if we have 5 data points and then our classifier makes 2 mistakes, so the total error in this case, will be 2 over 5. Yeah. So that's the total error in this case. So So for any classifier with accuracy higher than 50%, the weight is positive. So the more accurate the classifier, the larger the weight. And then the third stage is we update the weight for each data point as follows. So we update the weight. So this is the third stage. We update the weight for each data point as. So here, this is the previous weight. So multiply the previous weight. Then here is yi times the exponential of. So this is negative theta m yi fx fmx. This is I here. So and then we divide this by zm, where zm is a normalization factor. This is a normalization factor. So remember, I said that the sample weights should always add up to 1. So for them to add up to 1, we need to divide them by the normalization factor. So in this case, if a misclassified case is from a positive weighted classifier, the exponential term in the numerator would be always larger than 1. Thus, misclassified cases will be updated with larger weights after iteration. So the same logic applies to the negative classifier. So the only difference is that positive, the only difference for negative classifier is that positive is that correctly classified samples will be updated with the larger weights. So it's just an inverse. So after the mth iteration, remember from our formula, we said that fx is equals to the summation from m is equals to 1 up to m theta mx, and then fmx, like this. So we are saying after the mth iteration, we can get the final prediction by summing up weighted prediction for each classifier. So we then sum up the weighted prediction for each classifier, and then we can then get our prediction. So thanks for watching, guys. I hope this video helped you a lot to reinforce your knowledge on AdaBoost. So if you find this video, please subscribe and click the notification bell on so that you can continue to receive videos like this, which I will release every week. Thanks for watching. Hello guys, welcome back to my video. So if you are new to this channel, please subscribe and turn the notification bell on so that you do not miss any of my videos. So in this video, I'm going to be talking about the k-nearest neighbor algorithm. So the k-nearest neighbor is a supervised learning machine learning algorithm as the target variable is known. So if you remember, a supervised machine learning algorithm, a supervised machine learning problem is where we give a function some features, and we also give it some labels, and then the function will learn from the features to map the features to the labels, so that if we give it a new feature, it will try to predict the new label. So the k-nearest neighbor is a non-parametric algorithm, as it does not make an assumption about the underlying distribution of the data, so of the data points. So the k-nearest neighbor algorithm is also considered as a lazy algorithm, as it does not have a training step. So later in the video, I will illustrate how the k-nearest neighbor algorithm works, so stay tuned. So what is k in k-nearest neighbor? So the k in k-nearest neighbor is a number used to identify similar neighbors for the new data points. So k k nearest neighbor takes k nearest neighbors to decide where the new data point belongs to. So let's take an example. So let's say you have moved to a new place and you try to find new neighbors. You try to find new neighbors who have similar hobbies and who have the same goals as you. So that's how the k nearest neighbor works. So you start by you first look at the neighbors who are near, and then if you find some of the neighbors who have similar hobbies and passion, then they'll be your nearest neighbor. So that's how the algorithm works. So this decision is based on feature similarity. So that's what I was explaining. If you and your new neighbors have similar goals and passion, then the k nearest neighbor makes its decision based on feature similarity. So there is a higher. So let's take a look at this graph. So this graph is the graph of the F1 score against the k value. So as you can see, when k is equals to 1, we can see when k is equals to 1, we can see that the F1 score is low, or the accuracy is low. But we can also see that when k is equals to 5, the accuracy is higher. So when k is equals to 5, our model is more accurate. So this means that when k is equals to 1, our model is overfitting. So overfitting is a scenario whereby our model is a scenario whereby our model learns about the training features but is unable to generalize when it's given new data. So it's like when you study for a test, and then let's say you cram examples, but when the test comes, you fail to generalize with the questions that are given in the test. So there is a higher error rate when k is equals to 1, hence the model overfits when k is equals to 1. So as we saw, the F1 score starts to drop for a higher value of k. The test set reaches a minimum error rate when k is equals to 5. As you can see, the accuracy increases when k is equals to 5, which means that it reaches a minimum error rate when k is equals to 5. So now let's take a look at how the k nearest neighbor works in terms of how the k nearest neighbor algorithm works in a classification problem. Oh, I'm sorry about that. So let's say we have this purple category. So we have this purple category with purple data points. And then let's say we have this green category. So in this case, the value of k is equals to 5. So let's say we want to find where this blue data point belongs. So what we do is we consider 5 nearest neighbors. So in this case, let's say, so let me just use the booklet with the blue card. So we consider, let's say we just consider 5 nearest neighbors. So let's say these are the 5 nearest neighbors. So these nearest neighbors, we consider them in terms of distance. So we consider them in terms of distance from this blue data point. So in terms of distance from this blue data point. So how do we calculate the distance? So these data points are vectors. So how do we calculate these data points? How do we calculate the distance? So we use two methods to calculate the distance, or two parameters. We have what we call the Euclidean distance. We have what we call the Euclidean distance and the Manhattan distance. Sorry. So this is the Manhattan distance. So let's first take a look at the Euclidean distance. So let's say we have two vectors in a Cartesian plane. So we have a vector p1, which is given by x1 and y1, and another vector p2, which is given by x2 and y2. So how do we find the distance between these two vectors? Sorry, the distance between those two vectors. So we first find the distance in terms of the Euclidean distance. So I'll just call the Euclidean distance ED. So the Euclidean distance is the difference of x2 minus x1 squared plus y2 minus y1 squared. So that's how we calculate the Euclidean distance between these two vectors. So this is how our algorithm calculates the distance. It uses the Euclidean distance. So I hope I've clarified how the Euclidean distance is used to calculate the distance between two points in a k nearest neighbor algorithm. So the second method is use what we call the Manhattan distance. So let's also consider our vector p1, which is x1, y1, and another vector which is with coordinates x2 and y2. So we first calculate the distance. First calculate the distance from this point to this point, which I will call A. We first calculate the distance of A, and then we calculate the distance of B, and then we add those distances. So first calculate the distance of A, and then we calculate the distance of B. So that's how the Manhattan distance calculates the distance between 2 points. So let's get back to our k nearest neighbor algorithm. So as we can see from our k nearest neighbor algorithm, we can see that we have 3 points which belong to the green class, and 2 points which belong to the purple class. So we can see that the green class has more. This blue point is the green class has more points as compared to the purple class. So our blue point belongs to the green class, since the green class has more neighbors. So we have 1, 2, 3 neighbors as compared to 2 neighbors. So the value of k in this case must be an odd number. Because if we say, let's say the value of k is 4, there will be a situation whereby we have 2 points from the green class and 2 points from the purple class. So this will cause confusion to our algorithm. So the value of k should always be an odd number. So now let us take a look at k nearest neighbor in terms of class of a regression use case. So in terms of a regression use case, the classes are, the data points are from the same class. So in regression, we just want to calculate a continuous value. So let's say k is equals to 5 in this case. So we want to calculate the value of this purple class. Let's say this purple class. So we consider 5 nearest neighbors. Let's say these are the 5 nearest neighbors. So what we do is what the k nearest neighbor will do in terms of the regression problem is it will calculate. So it will calculate the average mean of all the nearest neighbors. Of all the nearest neighbors. So it will calculate the average mean of all the nearest neighbors. So the average mean of all these nearest neighbors will be the value of this purple point. So thanks for watching, guys. I hope this video helped you a lot understand the intuition behind the k nearest neighbor algorithm. So in the next video, I'm going to show you how to implement the k nearest neighbor using Scikit-Learn library. Thanks for watching, guys. Cheers. Hello everyone, and welcome to my video. And if you have not yet subscribed, please subscribe and turn on the notification bell on so that you do not miss any of my videos. So today I'll be talking about linear regression. So in this first part of the series, I'm going to be talking about the linear regression with one variable. So let's say you are a machine learning engineer and then you are hired by a real estate to create a model that predicts the price of house prices based on the size of the houses in feet. So how would you do that? So in this case, we have two variables. We have the size of the house, which is measured in feet squared, and then we have the price in dollars, which is in thousands. For example, if the size of the house is 2,500 feet squared, then the price is 500,000. So we have this problem. So how do we create a model that helps the real estate company to predict the prices of houses based on the size of the houses? So the first thing we are going to take a look at the notation. So in this case, the notation is we are first going to take a look at the notation. So M in this series is going to represent the number of training examples. So this is the number of training. This is the number of training examples. And then X is going to represent the input features. y is going to represent the target variable. Over the output feature. So x is also called the independent variable, and then y is also called the dependent variable, since our output is dependent on the value of x. That's why it is called the dependent variable. So let's look at our data set. Let's say in this case, if we have 52 rows, so in this case the number of rows is 52. We have 52 rows, so the number of training examples in this case will be 52. So the number of rows in this case is 52. So let's take a look at this example. So in this case, I have made a graph. In this case, I have made a graph in which we have the price in dollars, which is on our y-axis. So this is the price, and then we have the size in feet squared, which is on our x-axis, or which is our x variable, our input feature. So the value of the price depends on the variable x, or the input features. That's why this is called the dependent variable. This is called the independent variable. So in this case, how do we create a model that helps the real estate to predict the price of houses? So let's say in this case we draw a line. We draw a line that separates our data set. In this case, we draw a line that separates our data set. So in this case, let's say if someone wants to buy a house from the real estate. Let's say someone wants to buy a house of size 2,500 feet. Let's say this is going to be 2,500 feet. Then in this case, our model is going to predict that the price of the house will be somewhere around 290,000. It will be around $290,000. So this is how linear regression works. So this is called linear regression. So this is a regression type of a problem where our output is a continuous variable. As you can see, the output is a continuous variable. The price is a continuous variable. So now, how do we represent our model? So to represent our model, we need to be hypothesis. So let me show you how the hypothesis works. So this type of problem was a supervised learning, where we provide our model with both the answers. We provide our model with the values of x and the values of y. We provide our model with answers. We provide our model with examples at the same time with answers. So in this case, we have a training set. So we have a training set, and then we feed the training set into a learning algorithm, which the learning algorithm, which was our linear regression model, which we created for our real estate company. And then the learning algorithm creates a hypothesis. So the hypothesis then predicts the estimated price. The hypothesis then predicts the estimated price from the size of the house, which was in feet squared. So H here, H represents the hypothesis. So what is a hypothesis? So in this case, a hypothesis takes an input. So H, the hypothesis, takes an input X and tries to estimate the value of Y. So in this case, X was the size of the house in feet squared, and then Y was the price. So in other terms, the hypothesis is just a function. So the hypothesis is just a function which takes in X and then predicts the value of Y. Or in other say, we can say that H maps from value of X's to Y's in this case. So now how do we represent the hypothesis? So to represent we represent the hypothesis as h theta of X is equal to theta 0 plus theta 1 times X, where theta is the parameter. So theta is the parameters. So we have theta 0 and theta 1. So I'm sorry for that. So in this case, theta is the parameter, and then as you can see, the hypothesis h theta is a function which takes in an input X and tries to predict the value of Y. So let's try to visualize our hypothesis graphically. So in this case, say the hypothesis, our hypothesis h theta X, which takes in a value of X, is equals to theta 0, which is a parameter, plus theta 1 times X. In this case, our hypothesis has 1x because this is a regression problem with only one variable, or a univariate regression model. So we are only considering, in this case, we're only considering the size of the house in feet squared. But as we progress, and as I'll progress down the series, I'll also show you how to create a linear regression model hypothesis with more than one variable. Let's say, for example, now we can determine the price of the house based on the location and also the size of the house in feet squared. So if we draw a graph, X and Y, so this is Y and then this is X, and let's say we have a points here. So what our hypothesis does is it tries to create a line that best fits our data set. So this line is the hypothesis. So this line is h theta. of x theta 0 plus theta 1 x. So this line is the hypothesis, which is also the linear regression model. So thanks for watching, guys. I hope you understood what linear regression is. So in the next video, I'm going to talk about the cost function for linear regression, or how we can best fit our line to our dataset so that we can make our predictions accurate. So thanks for watching, guys. So if you have not yet subscribed, please subscribe and turn on the notification bell so that you do not miss any of my videos. Cheers. So if you have not watched my previous video, I advise you to do so that you can understand what I will be talking about in this video. And also, if you have not yet subscribed, please subscribe and turn on the notification bell on so that you do not miss any of my videos. So if you remember from the previous video, we talked about a linear regression, where we talked about we were hired as a machine learning engineer to create a model which would predict house prices based on the size of houses in feet squared. So, and then later on in the video, we then came up with a hypothesis. So if you still remember, we came up with a hypothesis, which our hypothesis takes in a value of x and as parameters theta 0 and theta 1x. So our hypothesis takes in the values of x and then makes predictions based on the values of x. So in this case, the value of x was the size of the house, which was in feet squared. So in this video, I am going to talk about, so in this video, I am going to show you how the parameters of the hypothesis, how the parameters affect how the parameters of the hypothesis affect how we best fit our line into our dataset. So if you still remember, this is the hypothesis, where we have the parameter theta 0 and theta 1. So in this case, we have the parameter theta 0 and theta 1. So let's take, for example, let's say theta 1 is equal to 0, and then theta 0 is equal to 2. So we want to visualize how our line would look like. So here on the x-axis, the x-axis takes in the values of x, and then the y-axis is h theta of x. So we want to plot a graph of h theta of x against x. So let's say here it's 1, here is 2, so in this case, let's start with when x is equals to 1. So when x is equals to 0. So in this case, we know that our value of theta 2 of theta 1 is 0. So this whole value is 0 since theta 1 is 0. So when x is equal to 0, in this case, h theta of x will be equal to 2. So h theta of x will be equal to 2. And then let's say when x is equal to 1, so if you substitute here, when x is equal to 1, then h theta of x is equal to 2 when x is equal to 1. So, and then when x is equal to 2, when x is equal to 2, you also find that h theta of x is equal to 2. So h theta of x is equal to 2. And then in this case, our hypothesis would look like this.
So this is how our hypothesis looks like when the value of theta 0 is equals to 2 and the value of theta 1 is equals to 0. So let's take a look at the other scenario. So let's say we know that our hypothesis h theta of x, our hypothesis h theta of x is equals to theta 0 plus theta 1 x. So let's say in this case theta 0 is equals to 0, and then theta of and then theta 1 is equals to, let's say theta 1 is equals to 1.5 in this case. So let's then draw, so this is x, this takes in the values of x, and then the y-axis, is going to take in the value of h theta. This will be h theta of x here. So let's then put in the values on the axis. So in this case, let's start with when x is equals to 0. So when x is equals to 0, that means that our hypothesis h theta of x is also equal to 0. So it's also equal to 0. But when x is equals to 1, h theta of x is equals to 1.5. So 1.5 is somewhere around here. So when x is equals to 2, if you substitute 2 here, if you substitute the value of x with 2, multiply 2 by 1.5, that's going to give you a value of 3. So you know that 3 is going to be somewhere here. So in this case our hypothesis would I'm sorry about that. So here, and then this is 1.5 here, somewhere here, and then 2 and 3 somewhere here. So in this case our hypothesis would look somewhere like this. Oh, I'm sorry about my drawing, but the hypothesis would look somewhere like this, and it would pass through the point 2 and 3, 1 and 1.5, and 0 and 0. So in this case the hypothesis would look like h theta of x, this is our hypothesis, plus theta 1 x. So by the previous two examples I've drawn here, I wanted to just show you how I just wanted to show you how the values of theta 0 and theta 1 affects how we fit our line to our data set. So in linear regression, to come out with values of theta, we want to come out with values of theta 0 and theta 1 that best fits our data set. So we want to choose the values of theta 0 and theta 1 that best fits our data set. So I'm just going to draw an example. So if you are familiar with linear algebra in high school, you knew that we used to draw in high school. You used to draw a linear regression or something like this. If you have a line, something like this, and then let's say your line passes through. I'm sorry about that. So let's say if our line passes through here, and then we know these are the, let's say these are the actual values. These are the actual values. So let's say this is our hypothesis, h theta of x. So this is our hypothesis, h theta of x, theta 0 plus theta 1 of x. So let's say this line is what our hypothesis is predicting, and then we know that these are the actual values of y. These are the actual values of y. Let's say this is y1, y2, and then y3. So to calculate the error, made by our hypothesis, in this case, so this is the error made by our hypothesis in this case. We subtract, let's say if it's y2, we subtract y2 from there. Sorry. We subtract y2. This is y2. Oh, I'm sorry about that. In this case, we subtract y2. In this case, we subtract y2 from what the hypothesis predicted. H theta of x. So that's how we calculate the error. If you still remember in linear algebra, so that's how we calculate the error. And also the same applies here. We subtract y3 from what our hypothesis predicted, which is h theta of x. So that's how we calculate the error. So this leads us to what we call the cost function. So this leads us to what we call the cost function in the cost function for. So let's say you are a driver and then you are drinking and driving. So if you are drinking and driving and then you are stopped by the police, and then they ask you to breathe onto a breathalyzer, and then they discover that you have a certain percentage of alcohol, there are high chances that the police is going to penalize you for doing that. So that's what happens with linear regression. So we want to penalize our model when it's making incorrect predictions. So we want to penalize our model so that it makes correct predictions. So in this case we are solving a minimization problem. So we want to minimize. So theta 0 and theta 1. We want to minimize theta 0 and theta 1. We want to minimize the difference between what our hypothesis is predicting, h theta of x. So we want to minimize the difference between what our model is predicting and the actual value. So we want to minimize the difference between the hypothesis and the actual value of y. So what we do here, we minimize this and then we square it, and then we want to find the summation, the sum of this. We want to minimize the sum of this from I is equals to 1 up to m. So if you remember from the previous video, when we talked about the notation for linear regression, we said that m was the number of our training size. So in this case, it's going to be h of I minus y of I. So remember that I represents the ith training set. So this represents the ith training set. Let's say if we have values of x and y, let's say we say 1, 2, and then say 3, 4. These are the values of x and y. So x1, so in this case x1 is going to be 1, and then y1 is going to be 3, which represents the ith training set. In this case I is 1, so that's why I substituted 1 in this case. So now back to our cost function. So back to our cost function. I said I said that the goal was to minimize the difference between our hypothesis and the actual value of y. That's the goal. That's our goal. So here, and then we divide it by 1 over 2m, where m is the number of is the size of the training set. It's the size of the. So this summation sign means that we are just going to sum all the values of of h theta and yi. So this summation means, let's say, I'm just going to explain to you. So if you don't understand what this summation means, it's just an addition. Let's say if you say y is equal to the sum from I is equals to 1 up to 4 of 2x. So what the summation does is, let's say it's y is equals to, if we substitute 1 here, it's going to be 2. And then let's say when I is equals to 2, then it's going to be 4. When I is equals to 3, then it's going to be 6. When I is equals to 4, then it's going to be 8. So what this means is that we are going to sum from I is equals to 1 up to when I is equals to 4. So this is the maximum when I is equals to 4. And then the total summation in this case is going to be 6, 12, 20. So y is equals to 20. That's the total summation. So this is what this summation sign represents. So this cost function is represented by j. So in this case, it's going to be j theta 0 and theta 1. So the cost function is a function that takes in the values of theta 1, theta 0, and theta 1, and it's going to find the suitable values of theta 0 and theta 1 which best fits our data set. So that's what this cost function does. So it's going to minimize. So it's a minimization problem, since we are going to we are minimizing the distance between the predicted value and the actual value. So theta 0, theta 1, 1 over 2m. Then we are going to sum from I is equals to 1 up to m from h theta of x I minus y I squared. So that's what the cost function does. So in this video, I just wanted to show you how the values of how the parameters of the hypothesis theta 0 and theta 1 affects how we best fit our data set, and how we can use the cost function to penalize our model. So in this video, I just wanted to introduce you to the cost function. So in the next video, I'm going to go deeper into the cost function, and I'm going to introduce you to another concept called the gradient descent, which we use to find the values of theta 0, and theta 1, where the difference between our predicted value and the actual value is minimum. So thanks for watching, guys. I hope you enjoyed the video. So if you find this video useful, please subscribe and turn on the notification bell on, so that you do not miss any of my videos. And also, you can share this video with all your friends. Thank you very much.
Hello guys, welcome to my another video on random forests. So random forests are a group of decision trees. So the problem with decision trees is that they work great with the data used to create them, but they are not flexible when it comes to classifying new samples. So last time when we talked about decision trees, we saw that when we are using a decision trees, we fit all the features into our decision tree, and then we train our decision tree, and then we make our decision tree to make predictions. But when we are using a random forest, like, it's only a subset of our features is fed into a decision tree. Is fed into a single decision tree, and then another subset of our data set is fed into another decision tree. So you can find that there is a variety in random forests, which makes them better than decision trees. So random forests combine the simplicity of decision trees with flexibility and resulting in a vast improvement in accuracy. So let's take a look at this data set. So here we are supposed to predict if a patient has heart disease based on these on these features. If the person has chest pain, sorry, this should be good blood circulation, blocked arteries, weight, and heart disease. So when we are creating a random forest, let's consider these features. Let's say we have chest pain, blood circulation, blocked arteries, and weight. So to create a random forest, let's assume that we randomly pick two two data points in our features, and then we use them to create a single decision tree. Let's say at first we use chest pain and then end with blood circulation, and then we use this to ask questions on our root node. Let's say chest pain, and then we then ask questions on our or then make questions ask questions on our decision tree. So in this case, let's say if someone has chest pain, yes or no, and then we then go on to pick other two random data points in our in our data set. Let's say we pick blocked arteries and then weight, and then we ask ourselves a question. Let's say here we have the weight, and then we ask ourselves another questions based on weight, and then let's say the next time is we are going to create another decision tree in a random forest, but now we are going to randomly consider other two data points. Let's say this time we're going to consider blocked arteries and weight. So let's say we are going to ask questions on our root node based on weight, and then we then split our decision tree. So and then let's say next time we pick another two random data points in our data set. Let's say we are going to pick blood circulation and weight, and then let's say going to ask questions on our decision tree based on blood circulation, on good blood circulation. So let's say GBC, and then we then create our decision tree. So that's basically how random forest work. So we can keep on doing this up to 100 decision trees. So as you can see this, that we have a variety of decision trees in our random forest, which makes them better than a single decision tree. So so the next thing I'm going to talk about is going to be ensemble. So ensemble learning in machine learning is a method that makes predictions based on a number of different models. So let's say, for example, the random forest algorithm is an example of ensemble learning, as the model uses a bunch of decision trees, different decision trees to make predictions. And then there are two types of ensemble learning. There is pegging and then there is boosting. In pegging, we train a bunch of individual models in a parallel way, and then each model is trained by a random subset of the dataset, as I've demonstrated in the previous, as I've demonstrated here. We're using a subset of our features to to train our model, and then there is boosting. So boosting is training a bunch of models in a sequence, and then each model learns from mistakes made by the previous model. So, so in this case, we are going to be talking about the random forest, which is an example of a pegging. And then boosting, we are going to, in the next video, I'm going to talk about other boost. So here in this example, we are going to use scikit-learn to predict if someone has a heart disease based on a dataset that I've downloaded on Kaggle. So the first thing is we are going to import our libraries, and then we are going to load our dataset into pandas. Then we are going to print our dataset. As you can see, we have age, sex, chest pain, and then we have things like ECG, and then the slope, and then we are going to describe our data set, and then we are going to display our columns, and then we are going to for our features we are going to take all the columns except the last one. The last one determines if someone is a heart disease, a yes or no. So this is the target variable. So our in our y variable, we are going to take the last column, which is the 13th column, which is our target variable. And then the next thing is, as you can see in our data set, we have these which are written not a number. So these are missing values. So sometimes when we are collecting values, some values will be missing. So we need to deal with those missing values in order to get accurate predictions in our model. So what you can do is we can import imputer from the scikit-learn library, and then we can then create an instance of our imputer, and then we pass in the argument missing values is not a number, and then the strategy is mean. So we are going to replace all the missing values with mean, and then we are going to replace them along the columns, and then we then fit our we then fit our features into the imputer, and then in the here we're going to transform our values using the imputer. And then the next thing is, as you can see here, we have different values. Some are ranging from 293, some are from 0.96, some are 1, some are 0. So for our model to make accurate predictions, we need to scale our values from a scale of 0 up to 1, so that our values, if are on the same page, so that our model is not biased towards certain values. So to do this, we import the standard scalar library from the scikit-learn, and then we then create an instance of the standard scalar, and then we fit our x values into the standard scalar, and then we scale our values. And then the next thing is we need to train our algorithm. We need training data. So we are going to split our variables. We are going to split our data set into a training set, a test set, and a test set. So our test set is going to be 20% of the whole data set, and then the training set is going to be 80% of the whole data set, as we want more examples for our algorithm to generalize well. And then we are going to use the test set to evaluate our algorithm on a data set which our algorithm is not familiar with. So to so choose random forest classifier from the scikit-learn library. We just import from sklearn.ensemble. So as you can remember, I've said that ensemble is a machine learning model that combines different models in order to make predictions. So here we're importing from ensemble, and then we are importing the random forest classifier, and then we are going to create an instance of the random forest classifier, and then we are going the number of estimators, or let's say the number of decision trees is going to be 100 of them, and then we are going to fit our model, and then we fit our training set, and then the labels for our training set, and then here we are going to evaluate our model on the test set, a data set which the model is not seen. So as you can see, our model is an accuracy of 100%. So sorry, our model is an accuracy of 86%, which is good. And then here we're going to make prediction. We are going to plot a confusion matrix. So what a confusion matrix does is it's going to show us, evaluate how our model made predictions, if our model made the right predictions or if our model made the wrong predictions. So as you can see, we have the true positive, false positive, we have the false negative, and then the true negative, and then the true negative. So as you can see that our model classified 35 people correctly as having a heart disease, and then 5 people wrongly classified as to having a heart disease when they don't, and then 3 people were wrongly classified as not having a heart disease, but these 3 people were classified as not having a heart disease, but these people have a heart disease, and then 16 people were correctly classified as not having a heart disease. So thanks for watching, guys. If you like the video, please hit the like button and the notification bell and the subscribe button so you can get more videos like this. If you guys are not familiar with the concept of a decision tree, you can check out my previous video. Also, if you have any suggestions, please put them in the comment section below. Thanks for watching, guys. Cheers. Another video. In this video, I'm going to show you how to deploy a random forest model or in a scikit-learn model into Flask. So in this case, we are going to use our model we created in the previous video to predict house prices, but this time we are going to deploy it into a Flask web application. So as you have remember, I've created this random forest model. So in order to deploy the model, I must first save my model into my local disk. So to do that, I imported joblib, and then to save the model into my local disk, I then dumped the model using the dump function. Then I passed in my model, and then I passed in the name of the model that I want to be saved into the disk. And then as you can see, the model is then saved into the disk. So as you can remember, when we were predicting house prices, we used different features. We used like the rooms, bathroom, length size, latitude, longitude, distance, car, length size, and building area to train our model, and then to predict the price based on these different features. So we are going to use these features. We are going to use these features to predict the house price. So 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 the next thing is, this is my project structure. So here I have templates. So templates are just views. So this is going to be our user interface, which will allow our user to enter to enter commands into our web application. And then I then have the model, which is the house price model, which I saved from my Jupyter notebook. And then the next thing is the CSS, which I am going to use to style my model. Then the next thing is the app, this Python file, which is going to contain different libraries such as pandas, flask, and joblib. So this is the project structure. So to deploy my web application, so the first thing is I created a user interface using HTML. So these are the forms which the user is going to enter the to enter our features. So yeah, this is going to be an input form for rooms. This is going to be an input form for bathroom, input form for length size, and then for latitude, longitude, distance, car, and so forth. And then we have this div here. So this is going to display different. This is going to display predictions made by our model. So the next thing is I'm going to. This is this is our Python file, which is going to have Flask, and then which is going to have our model, and this is where predictions are going to happen. So we are going to use Flask to create a local server. So what is going to happen is, when our user enters details into our user interface, those features are going to be sent to our server, let's say our local server, via what we call, it's going to be a request. So we are going to send a request to our model, and then our model will run inference or predictions, and then our model will then send back a response, and then that response is going to be displayed to our user interface as predictions. So here I imported Flask, and then I imported pandas, which we are going to use for data pre-processing. Then I imported joblib so that I could load my model into our web application. So to do that, I then opened my model, and then saved I then saved the model this variable f, and then here we are going to load the model from we are going to load the model. And then the next thing is we are going to create an instance of the flask class. So then we are going to pass in this name, and then we are going to pass in the template folder. So is this template folder is our main.html, which is going to be our user interface. So we are going to pass it into our instance. The next thing is we are going to create this route, and then we are going to pass in methods, which is the get and then the post. So the post is used, let's say, when our user interface enters data into our form. The data is then sent to the server via a post, and then to get a response, we then use the get method. So if you guys are not familiar with this is a REST API. You can go on Google and then search for REST API. And then the next thing I did was I created a function, which is the main function. And then in this main function, the first thing we do is we check if our request, that we are going to make to our server or to our model is a get. So if our request is a get, then we are going to return this user interface, our HTML file, which is the main.html. But if our request is a post, so that means that we are going to send a request to our server. We then retrieve this data from our HTML form. As you can remember, this we created HTML forms so that our user can enter like the number of rooms, then like the bathroom, and then the length size. So here we are now retrieving the values from that our user entered from the forms. So here we are going to retrieve the rooms, bathroom, and then the length size. So in order to retrieve this, you should make sure that this value rooms matches this value, matches the name in our input form. These two should match, otherwise you would get an error. And then the next thing is, after we've done that, the next thing we are going to do is we are going to create our input variables, and then we are going to use pandas to create a data frame, and then we then pass in our values that we retrieved from our forms. The next thing is we are then going to create columns in our data frame. So these columns should correspond to the data that we retrieved from our HTML form. And then the next thing, you are going to specify the data type, which is going to be a float. And then the next thing is we are going to specify the index as input. So the next thing is we are going to make predictions. So here, the predictions, we are going to make predictions, and then we are going to pass in the input variables that we got from our HTML form to our model, so that our model can return can make predictions. The next thing is we are going to print predictions, and then the next thing here we are going to return flask, and then we render our user interface or our template, and then we are going to create a dictionary, which is going to be original input. So here we have the room. We are going to So the rooms will correspond to the number of rooms, bathroom to bathroom, and then length size to length size. So the reason why we will pass this to the original input is we are going to loop through these values, and then we are going to display them on our user interface. And then we then create a variable result, and then we equate this variable result to we then set this variable result to our predictions. So this variable result that we set to our predictions, we are going to retrieve this variable to our user interface. So you make sure that every variable that you pass through the render template is we can retrieve this value via our HTML. So once we've done that, I've created this div, and then I've created this class result. So, and then this syntax is called Ginger. Yeah, it's a Flask syntax that you can use to pass in variables, and then so you can pass in your Python logic into this syntax. So you can check out the Flask documentation. You just Google Ginger Python, and then it will show you. So here we are going to specify if the result, and then we are going to look through the variable. We are going to look through the variable and the value in our dictionary, and then we are going to print out the variable let's say price, and the predicted, let's say the variable is price, and then we are going to print out here the value of the price. And then the next thing is we are going to display the predicted house price, and then here in this paragraph we are going to display the result. So that's how you deploy your Scikit-Learn or a random forest module into a Flask web application. So to run this application, we first start the command line, and then we just type Python app.py. As you can see now, our server, our server is on. So, and then our server is running on localhost on port 5000. So let's go to localhost and specify the port it's 5000. So I don't know why it's taking long, but it should have. Okay, guys, let's restart the server. Okay, so the application is started. So let's say you want to predict the house price for a house with 12 rooms, let's say with 3 bathrooms. Let's say the land size is, let's say, 5,000 square meters. Then latitude, let's say it's at 7. Then the longitude is 144. And let's say the distance is 145 kilometers. And then the number of cars, let's say, is 3. And then the land size, let's say 7,800. Then building area, let's say it's just, let's say 10,000 square meters. Then the year in which the house was built, let's say the house was built in 2016. And then let's submit. So as you can see, guys, we have created our model. We have created a web application that predicts house prices using our Scikit-Learn Pipeline. I hope this video helped you a lot, guys. So I challenge you to look for a different data set on Kaggle or any other platform, and then you can then do data pre-processing, and then you can then model evaluation, and then I challenge you to create your own web application, guys. So if you've done so, you can, once you've done so, you can put the links in the description below so that I can see what you've done, guys. Thanks for watching. I hope this video helps you a lot. So may you do me a favor by hitting the like button and the subscribe button. Thanks for watching. Hello guys, and welcome back to my video. So if you've not subscribed to this YouTube channel, please make sure you subscribe and click the thumbs up button so that you help me create more content. So guys, I'm very sorry for not releasing content for the past few weeks. I've been busy with exams. So today we are going to look at the logistic regression algorithm. So let's first take a look at this scenario. So let's say you want to predict if a person is at disease based on their cholesterol level.
So one way of doing that would be to use a linear regression model. So if you have not watched my previous videos about linear regression, I advise you to do so that you can understand where this is coming from. So let's take a look at this. So let's say we want to predict if someone has heart disease based on their cholesterol level. So this is heart disease. So let's say we have these data points here, and these data points here. So one way of doing this would be to use a linear regression model, something like this. We use a linear regression model, something like this, and then after using a linear regression model, we can then use a threshold classifier. So if you remember, the hypothesis for our linear regression model was h theta of x is equals to theta transpose times x. So our threshold classifier will be if, let's say, if h theta of x is greater than or equal to 0.5, then we would predict that y is equals to 1, or yes, or the person has that disease. So if our threshold h theta of x is less than 0.5, then we would predict that y is equal to 0, or the person doesn't have heart disease. So this is the threshold, 0.5. So points on this right side are classified as 1. So points from this right side, these points here, are classified as a person who has these features are classified as a person who has heart disease, and then these features are classified as a person who doesn't have heart disease. But there is one drawback of using the linear regression model. So let's take a look at the drawback. So let's say that we have these data points here, and then let's say here we have these data points, and we have other data points that are further away. Let's say we have data points here. So let's extend our line up to somewhere here. So if we draw our linear regression model, that would be something like this. And then using our threshold that we used in the last example, this is the threshold. Let's say this is the threshold in our last example. You can see that now the linear regression model is now misclassifying some of the examples. You can see that this example is now being classified as someone who doesn't have heart disease, but this feature falls under someone who has heart disease. So how do we solve this problem? So to solve this problem, that's where comes in what we call the logistic regression. The logistic regression, or the logistic function. So let's first define the hypothesis for the logistic regression model. So the hypothesis for the logistic regression model is h theta of x is equals to G, our theta transpose, times X. So in this case, G is equal to 1 over 1 plus E to the power negative Z. So also we can, also that's G of Z. So we can substitute this into, Z. So that becomes G theta of T transpose X is equals to 1 over 1 plus E to the power negative theta transpose times X. So this is what we call this is the hypothesis for the logistic function. So let me draw the logistic. This is called the logistic function. So this is called the logistic function, or the sigmoid, function. So let me draw the graph for this function. So the graph for this function is something like this. So the logistic function is H-shaped. So this, the y-axis, represents our hypothesis H theta. Represents our hypothesis H theta is equals to G theta T transpose times X. So this axis represents negative Z, this axis represents positive Z. So Z ranges from negative infinity up to infinity. So this is the graph for the logistic function. So how does this logistic function solve the problem that our linear regression was making of misclassifying examples? So let's check this out using the example we used when we first talked about the linear regression. So we are trying to predict if someone has had disease. So it should be like coronary heart disease. So this is the cholesterol level. So if we draw these examples, then our logistic regression function will be something like this. So this is, so let me erase here, I made a mistake. So the logistic function will be something like this. It's sort of like S-shaped. I'm sorry about my poor drawing, but it's something like this. It's S-shaped. So what the logistic function does is predict if something is true or false. So this type of a problem we are trying to solve is called a binary classification problem, where we are trying to predict if someone is at disease or not. So we represent if someone is at disease, which is yes, we represent it by one. We represent it with 1. If someone does not have a heart disease, we represent it by 0. So what the logistic regression does is predict if something is true. It means if someone is at disease, that's 1, which is true. If someone doesn't have a disease, that's 0, which is false. So that's what the logistic function does. So the logistic function is S-shaped, and also this curve tells us the probability of someone having heart disease based on their cholesterol level. So this is the probabilities. These are the probabilities. They range from 0 up to 1. So what this curve does is it tells us the probability of someone having heart disease based on their cholesterol level. So let's say if we take this example here, let's say it's somewhere here. So let's say this is around maybe 0.8. So this tells us based on this cholesterol level, there's an 80% chance that this person is there's an 80% chance that this person has heart disease. So that's what the logistic function or this curve tells us. So in this case, so this is 0.5. So in this case, if the probability that a person has heart disease is 0.5, we classify that person as having heart disease. If it's less than 0.5, that person is classified as not having heart disease. So I hope you guys understood what is the logistic regression and how it is used to classify, how it is used to solve problems such as the binary classification problem. So in this case, we only used one feature, but logistic regression can also have multiple features. We can also determine if the person is heart disease using the cholesterol level, the weight, let's say the weight, and then let's say we can also use the blood pressure, and then we can also use the chest pains, if the person has chest pains, to determine if the person has heart disease or not. So thanks for watching, guys. I hope this video helped you understand more about logistic regression. So if you have not yet subscribed to this YouTube channel, please subscribe and turn on the notification bell on so that you don't miss any of my videos. Thanks for watching, guys. Cheers. My video. In this video, I'm going to show you how to predict if a person has coronary heart disease using logistic regression, but we'll be using a Python library called the Scikit-Learn Pipeline. So as you can see, the World Health Organization is estimated that there are 12 million deaths occur worldwide every year due to heart diseases, and then half of these diseases are in the United States. Other developed countries are due to cardiovascular diseases. So the early diagnosis of cardiovascular disease can aid in making decisions on lifestyle changes in high-risk patients and in turn reduce the complications. So let's say you are being hired by a hospital to analyze their data set and then to predict if someone has a coronary heart disease, and then this will help the doctors sort of like give the patients medication or tips on how to change their lifestyle and diet so that they can reduce the risk of dying with heart attack. So the first thing we're going to do is we're going to import libraries such as pandas, which we are going to use for exploratory data analysis. We are going to use NumPy, which is a mathematical library, and then SciPy, which is used for statistics, and Matplotlib, which is used to visualize the data set. So here, this is my folder where I have I have this CSV file with framing arm. I got this file from Kaggle, and then here we are going to read the data from this file. We're going to read the CSV from this file, and then we are going to drop this column return education, and then we are going to use this dotted function from the pandas library to display the first 5 items in our dataset. So in our dataset we have these variables. We have the demographics, which show sex, which show if male or sex, which shows us if someone is male or female. We also have the age of the patient, so this is continuous, although ages sometimes are represented by whole numbers. And then we have like behavioral variables, like current smoker, whether if a person is a smoker or not. We also have the cigarettes per day, so these represent the number of cigarettes that the person smokes per day, averagely per day. And we also have like medical history, like whether or not the patient medical history, or BP meds, whether or not the patient was on blood pressure medication, like prevalent stroke, whether or not the patient had previously had stroke, like prevalent hype, whether the patient was hypertensive. And then we also have diabetes, whether or not the patient had diabetes. We also have the medical current, like the current information, like the total cholesterol level, which is a continuous variable. And then we have the systolic blood pressure, which is also a continuous variable. We have the diastolic blood pressure, which is also continuous. We have the body mass index. So the body mass index measures the obesity of someone. So, and then we have the heart rate, which is continuous, which is a continuous variable. We also have the glucose level. We also have the predict variable. So 10-year risk of coronary heart disease. So this is a binary classification type of problem. So if you have watched my previous video where I explained about the logistic regression, you should understand what is a binary classification problem. So a binary classification problem is a problem where we try to predict if something is positive, we represent it by 1. If something is negative, we represent it by 0. So in this case, if something has coronary heart disease, we represent it by 1, which is yes. If it doesn't have coronary heart disease, we represent it by 0, which is no. So now we are going to rename this column, the male. We are going to rename it as sex male. And then here we are going to check if there are any missing values. As you can see that on the cigarettes per day column, we have 29 missing values, and on the blood pressure we have 53 missing values. On glucose we have 388 missing values. So here you can see that here we want to visualize the total number of missing values. You can see that the total number of missing values is 489. So since it is only like 12% of the entire dataset, the rows with missing values, we then exclude it. We then drop these missing values, since they only constitute of 12% of our dataset, which is almost like negligible. So the next thing is we want to visualize our features. So here we have the sex male distribution. So here you can see that the distribution of heart disease is highly distributed on males and lowly distributed in females. And you can also see on the current smoker distribution, you can see that there are more males that are smokers than females. And you can see that we can also visualize the cigarettes per day, and you can see that they are also missing values. So we want to see if our data set is balanced. So as you can see, our data set is unbalanced. We have almost like 3,000, maybe it should be 3,200 examples, which show that 3,200 examples which show that they are negative negative examples, and we have almost like 500 positive examples. So we then visualize our dataset. We then use the describe method from the pandas library to describe our dataset. So now we move on to logistic regression. So logistic regression is a type of regression analysis and statistics used for prediction of outcome of a categorical or dependent variable from a set of predictor or independent variables. So if you want to know more about logistic regression, I advise you that you watch my previous video where I explained logistic regression from scratch. So here we just want to see the statistics. So here we import the Scikit-Learn library, and then we then create these features, new features. So these features contain the age, the sex, the cigarettes per day, the total cholesterol content, the systolic blood pressure, the glucose, and then the 10-year chronic heart disease feature. And then in this case we then chop off the last column, which represents the last column, which is our label, so these labels will represent if someone is heart disease or not. And then on the y, we then assign these labels on the y variable here. And then we then import from model selection from the Scikit-Learn library the train test split, and then we then split our dataset into training set and test set. So we split our dataset into 80% training set and 20% test set. And then we then import the logistic regression. We then import the logistic regression from the Scikit-Learn library, and then we then create this instance of the logistic regression, and then we then fit our training set into our logistic regression, and then we then predict this y value from the logistic regression, then predict from our test set. And then we then import Scikit-Learn matrix to see our accuracy score, and then you can see that our model is 88% accurate. And then we then display this confusion matrix. So what this confusion matrix does is, here it shows us the true positives. So the true positives are people who were predicted as having heart disease, and they actually have heart disease. So there are 658 true positive cases, and this which is represented by 4 is the true negatives. So these are people who were predicted as having heart disease, but they do not have heart disease. And then we then have the false positive. We then have the false negative. So the false negatives are people who are predicted as not having heart disease, but they actually have heart disease. And then we have the false negative. So these are people who are predicted as not having heart disease, but they actually have heart disease. So in this case, our data set was imbalanced. So we do not use accuracy as a measure. We do not use the accuracy as a measure of how well our model is performing. We use other methods such as specificity and recall. So as you can see here, we then import the binaries from the Scikit-Learn library, and then we then lower our threshold. We try different thresholds. For a threshold of 0.1, the confusion matrix is this. So if you have understood what I've said about true positive and false negatives, but in this case we want to maximize the likelihood of predicting if someone has a disease. So in this case
our most important, we want to see if someone is a disease which is true positive. So we want to maximize that likelihood of someone having a disease. And then you can see with threshold of 0.2, we can see that the true positive is increased. When we have the threshold of 0.1, the true negative was 240. With the threshold of 0.3, we can see that true positive is 617. With the threshold of 0.4, the true positive is 652. And we can then plot what is called the receiver optical character curve. So what this does is there should be a line here that ranges from here up to here. So the further this line is away from the line, that a diagonal line, if you draw a diagonal line, something like this. So if this curve is further away from the diagonal line, then the more accurate our model. So as you can see here, the accuracy here, the ROC accuracy score is 73%. So we can increase this accuracy by tweaking or playing along with the parameters, but I will leave that to you. You can research on the Scikit-Learn documentation to see how you can improve the accuracy of the logistic regression model. So thanks for watching, guys. I hope this video helped you understand how we can use the logistic regression model to predict if someone is at. Hello guys, and welcome back to my video. In this video I'm be talking about Scikit-Learn pipelines. So Scikit-Learn pipelines is a class that allows us to encapsulate all our transformations and our final estimator. So what the pipeline does is applies a list of transforms and final estimator, and the intermediate step of a pipeline must implement fit and transform method, and the final estimator only needs to implement the fit. So what it does is the pipeline class is also similar to other Scikit-Learn classes that we've seen, such as the support vector machines and so forth. They all have similarities. As you can see that the Scikit-Learn pipeline also has the fit, the predict and score, just like any other estimator that we use using the Scikit-Learn library. So the step parameter for the pipeline must be a tuple consisting of a name and an instance of the final estimator. So what the estimator does, what the pipeline does, it makes us easier for us to fit our classifiers. So let's say we want to create a model. Let's say let's say to predict fraudulent transactions in credit cards. So as a machine learning engineer, as you'll be developing this model, there's a chance that you want to test different models. Let's say, for example, you want to test your data on the support vector machine, logistic regression, the k-nearest neighbor, gradient boosted trees, and other traditional machine learning models. So what you do is the pipeline allows us to fit estimators such as the standard scalar, or like principal component analysis that we use to decompose dimensions. So the principal component analysis works just, let's say if we have data that is like 30 dimensions, the principal component analysis allows us to break that data into something which is simple, let's say two dimensions. So that's what the pipeline does. So now I'll walk you through the code and explain how to implement the pipeline in Scikit-Learn. So just know that the pipeline is just an encapsulator that makes us easy for us to fit all our estimators, such as the standard scalar, like principal component analysis, like grid search for improving our parameters for different models. So the first thing is we import the iris dataset from Scikit-Learn, and then the next thing is we import the model. We import train test plate from Scikit-Learn.model selection. We also import from the Scikit-Learn preprocessing. We also implement the standard scalar. So what the standard scalar does is that in our dataset we have different features. So these features have different values. Some features have way big values than other features. So what So what the standard scaler does is that it subtracts each feature. Let's say it subtracts the value of x, let's say from the mean, and then it then divides that value by the standard deviation. So if we apply the standard scaler, we find that our data set maybe will be falling along the same range. So we want our data set to be following along the same range, so that our model will not be confused. We also, from Scikit-Learn decomposition, we also implement the principal component analysis, which is PCA, which I've also talked about. We also implement from the pipeline. We also implement the pipeline instance or the pipeline class from Scikit-Learn Pipeline. We also implement the job lib. Which we are going to use to dump our sklearn final model, so that we may use it maybe for production. Maybe if you want to create a web application, or you want to deploy it into maybe an Internet of Thing application. So our first model, we are going to from linear model, we are going to import our logistic regression model. And then from scikit-learn.ensemble, we're going to implement the other boost classifier and the gradient boosting classifier. So ensemble is just these are a group of models that have been grouped together, so that each model learns from the mistake that is made by another model. And then from scikit-learn.neighbors, we also implement the k-nearest neighbor class. And then we also implement the support vector machine. So the first step is we load our data. We initialize our data set. So iris is equals to load iris. And then the next step is we are going to split our data set into training and test set. So here we have the x value for the train set, x value for the test set, y value for the train set, y value for the test set. And then it's just equal to, and then we initialize this class, the train test split, and then we provide the first parameter should be our features. So in this case, this is iris.data, and then the next value should be our labels or our target, which is iris.target. And then we want to split our data set. 20% of our data set into test set, and then 80% of our data set into training set. So this test set parameter allows us to split our data set. Allows us to split our data set into a test set. So we provide 0.2, which is 20% of our data set, and then we randomize our data set. So here we are going to initialize the pipeline class. So the pipeline class takes in a parameter of steps. So the step parameter for pipeline must be a tuple consisting of a name and an instance of the transformer. As you can see here, the step parameter for the pipeline must be a tuple consisting of a name and an instance of the parameter or estimator. So as you can see here, we initialize the pipeline LR, which is for logistic regression, and then we initialize the pipeline class. We then provide a tuple. If you remember what I said the first thing is the name of the transformer or the estimator class. Here the name is SCO, which is standard scaler. Here we'll provide the tuple name SCO, and then provide the transformer, which is the standard scaler. Here it's PCA, which is principal component analysis, and then we initialize the transformer, which is PCA, and then we want our number of dimensions or number of components to be 2. So this is the parameter n components is equals to 2. CLF, which is our classifier or our estimator, is we initialize it as logistic regression. We randomize it to 42. The next thing is we create also a pipeline step for the support vector machine, and then we initialize the pipeline class, and then we provide this tuple. We first provide the name of the transformer, which is SCO, which is standard scaler. We initialize the standard scaler class, as you can see. The next thing is we also provide the name of the transformer, which is the principal component analysis. We provide the instance of the class of the principal component analysis. The number of components is equal to 2. Also, now here we put the final class, the name of the estimator, CLF, which is support vector machine dot support vector classifier.
we randomize it to 42. The next step is we we create a variable for the step for the decision tree pipeline. We initialize the pipeline class. We also do the same thing. We start with the name of the transformer, which is standard scalar. We initialize the standard scalar class. We also put the name of the next transformer, which is the principal component analysis, which is PCA. We initialize the PCA. Number of components is equals to 2. The third part is we initialize our estimator, which is CLF, and then we initialize the decision tree classifier class. We randomize it to 42. The next thing is we also create a step for the other boost algorithm. We initialize the class as we have done above. Provide the first name of the transformer. We initialize the class of the transformer, which is standard scalar. We do the same thing for the principal component analysis. We first provide the name. We initialize the class or the instance of the principal component analysis. We provide the number of components, which is 2. Now we provide the name of the estimator. We initialize the class of the estimator, which is other boost. We do the same thing for the gradient boosting algorithm, and we also do the same thing for the k nearest neighbor algorithm. Now the next step is we create a list of pipelines so that we can easily iterate through them. So what we do here, we create an array or a list. This array, we call it pipelines. We first provide the pipeline step, or first provide the pipeline step for the logistic regression, the pipeline step for the support vector machine, pipeline step for the decision tree, pipeline step for the other boost, pipeline step for gradient boosting, pipeline step for k nearest neighbor. And then we then create a dictionary of pipelines and classifier type for ease reference. So our first here, the key here is 0. The value is logistic regression. The second key is 1. The value is support vector machine. The third key is 2. The value is decision tree. The fourth key is 3, and the value is other boost classifier. The fifth key is 4, and the value is gradient boosting. Now we iterate through the array that we have created. This array, we iterate through this array. So now, instead, what I really like about this pipeline is, let's say for instance we created different classifiers. Let's say we initialize different classifiers, let's say for other boost, support vector machine, decision trees, and so forth. That means that we would need to fit our data set separately for each estimator. So what I like about the pipeline is that instead of fitting our data set separately for each estimator, what the pipeline does is we only need to fit our data set into the pipeline, and this pipeline will now fit our data set in all our estimators. So this is how the pipeline makes it easier for us as machine learning developers to create machine learning pipelines or project. It encapsulates the whole process of repeating some of the things, and makes it easier for us to just fit something once, and it will be fit on all our classifiers. As you can see here, we iterate through our pipelines list, this list that we have created, and then we fit our dataset into the our pipeline list. So that means that our dataset will be fit to the logistic regression algorithm, support vector machine, decision tree, other boost, gradient boosting, and k nearest neighbor. And now the second step is we need to compare accuracies. So what we just do is we just loop through the pipelines. As I've said, that the pipeline is all the methods, such as other estimators, such as score. As you can see that the logistic regression algorithm has an accuracy of 93.3. Support vector machine has an accuracy of 90.0. Decision tree pipeline has a test accuracy of 87%, other boost pipeline test accuracy of 0.60, gradient boosting pipeline a test of 87%. The K nearest neighbor is a test accuracy of 93.3%, which is also the same as the logistic regression algorithm. Now we want to identify the most accurate module on our test data. So let's say, like I've said in the beginning of the video, let's say we're creating an application, let's say for a bank, to detect fraudulent transactions. Now after fitting all your models and after doing all the pre-processing, now the final step will be you want to choose which model is best so that you can use that model for production. So you can see here, we first initialize best accuracy with 0, best classifier with 0, best pipeline as a string, and then we then loop through the pipelines, and then if the value dot score is greater than the best accuracy, then we want the best accuracy to be the value dot score, and then we feed our test set, and then we set the best pipeline variable that we have created to the value to this value, and then we best classifier to this index, and then we print the classifier with the best accuracy. After that, we save the pipeline to file, or we then save the pipeline to disk, so that you can use that for production. So now that I have explained, I'll just run this code so that you can see what is happening. As you can see, that our classifier with the best accuracy is the logistic regression. So thanks guys for watching and tuning in to my video. So I'll put the link in the description for the code, for the GitHub repo that is the code that I have used. Thanks for watching guys. Cheers. So in the next video I might talk about how to fit the grid search or the K-fold for improving the accuracy of our models. Thanks for tuning in guys. Cheers.
Hello guys, and welcome back to my video. In this video I'll be talking about cross-validation. So let's say you are a medical research scientist, right? And then your task is to find a cure for a certain disease. And then what you do is you research, and after researching is you test your cure on different animals before it is given to humans, right? The same thing happens when we do machine learning. So let's say we have an algorithm, and then we have an algorithm such as the K nearest neighbor, and then we train our algorithm on the training set, and then after that we then evaluate our algorithm on the test set. So what happens is that information on the test set sometimes may leak into our algorithm, thus forcing our algorithm to overfit on the test set. That means that our algorithm learns patterns on the test set, but when it is put for real world use, it fails. So what's the solution? The solution will be to create another data set for the validation set, right? So let's say we have created our data set for the validation set. We have split our data set into training set, test set, and then the validation set, right? So training is done on the training set, and then validation, and then we evaluate our algorithm's performance on the validation set. After that, the final evaluation of the model is then done on the test set, right? The problem with this is that when we divide our data set into 3 sets, is that our data set may end up with a little data set for us to train our algorithm. So what's the solution to this? The solution to this is the cross-validation set. So what happens with the cross-validation set is that we divide our data sets into K sets or K folds. We divide our data set into K folds if we are using the K fold cross-validation. So let's say we have 5 folds, right? We have 5 folds, and then on those 5 folds we then remove 1 fold. We train our algorithm on 4 folds,
and then we then evaluate our model using the one fold that we left. And then we then do the final evaluation using the test set. So that's the solution. So a model is trained using k-1 of the folds as training data. So let's say if we have 5 folds, our model is going to be trained using 4 folds as training data. And then the resulting model is then validated on the remaining part. So that part that we had left, we then use that to evaluate our model, right? So let's look into the code. So the first thing here is we are going to import NumPy, which is a mathematical library. And then we are going to import pandas, which we are going to use for data preprocessing. And then the next thing is we are going to import the iris dataset from Scikit-Learn datasets. And then we then create an instance of the iris dataset as iris is equals to load iris. And then our features is iris.data. And then our labels will be y is equals to iris.target. And then the next thing is we are going to normalize our dataset. And then the next stage is we are going to split our dataset using the train test split. So if you've watched my previous video, then you know that when we are creating machine learning algorithms, we split our dataset into a training set and then test set. So a training set that we are going to use to train our algorithm, and then the test set that we're going to use to evaluate the performance of our algorithm, right? So here we then split our dataset into training set and then test set. Here we have the X train and then the X test, the Y train and then the Y test. And then we split our dataset. And then we have a test size which is 30% of our total dataset. And then the next stage, the next stage is we are going to import from the Scikit-Learn library the k-nearest neighbors classifier. So if you are not familiar with the k-nearest neighbor classifier, I encourage you to watch my previous videos on the k-nearest neighbor. I have well-detailed videos on how the k-nearest neighbor works. So we have our k-nearest neighbor classifier, and then we have a total number of the neighbors. We have 3 neighbors, and then we are going to import from the Scikit-Learn again the model selection, and then we are going to import the cross-validation score. And then we are going to, this displays the accuracy of our k-nearest neighbor classifier. And then we then fit our k-nearest neighbor classifier into our training and test set. And then we then evaluate the score of the k-nearest neighbor on the test set, which is X test and then Y test. As you can see, the test accuracy is about 95.6%. So in order to improve our algorithm, there is another cross-validation method that I'm going to talk about. I'm going to talk about the grid search cross-validation method. So the grid search cross-validation method works like this. So we want, let's say, in the previous, when I explained above, we talked about the k-nearest neighbor, right? And then the number of neighbors, which is our parameter. The number of neighbors was 3, right? But this might not be the perfect parameter for our model. So what do? So we pass in a range of parameters on the grid search, right? From 1 up to 50. That's the range of parameters on the grid search, right? So what the grid search does is it goes through each and every parameters. As you can see here, we have grid is equals to n, which is number of neighbors, np.arrange from 1 up to 50. So we have parameters from 1 neighbor up to 50 neighbors, right? So what the grid search does is it searches first if the parameter is 1 and then calculate the score, then tests out the parameter if it's scored to 2 up to 50. So it goes through each and every parameter from 1 up to 50, and then it then finds out the best score for each of the parameters. So what the grid search does is it helps us to find the best parameter for our model. So here we pass in the dictionary number of neighbors, and then we pass in the range of parameters from 1 to 50. Then we then create an instance of the k-nearest neighbor class, and then we then fit in the k-nearest neighbor to the grid search algorithm. And then we have grid, which is this one, which we are going to pass the range of parameters. And then we have the cross validation, which is equals to 10. And then we then fit our data set into the grid search. So as you can see here, grid search has gone through each and every parameter from 1 up to 50. And then the next thing is we are going to print which parameter is the best. As you can see here, tuned parameter k neighbors is equal to 13. So the best parameter for our model is 13. The best nearest neighbors is 13. So for our k nearest neighbor to work, it needs up to 13 nearest neighbors, right? So if you are a little bit confused about the k nearest neighbor, I urge you to watch one of my videos on the k nearest neighbor, right? So now, what is the k-fold cross-validation? So k-fold is where a given data set is split into k number of sections, where each fold is used as a testing set at some point. Let's take the scenario of 5 folds. Let's say we have 5 folds. Here, the data set is split into 5 folds. In the first iteration, the first fold is used to test the model. The rest are used to train the model. In the second iteration, the second fold is used as the testing set, while the rest are used as the train set. The process is repeated until each of the 5 folds has been used as testing set. So what this basically means is that here we have our data set. And then let's say the k-fold number of folds, we have 5, right? So here we are going to leave out the first fold, this one. We are going to leave this one out. And then we are going to use these 4 folds, to train our algorithm. Once our algorithm is trained, we then use this fold, the first fold that we left, to evaluate our algorithm, or our machine learning algorithm. After that, the next stage is we have again 4 folds, right? And then here, the second, we are going to leave out the second fold. Remember, previously we left out the first fold, but here we're going to leave out the second fold. We train our algorithm on these 4 folds, 1, 2, 3, 4, with green colors. And then we then evaluate the performance of our model using fold number 2. The process is repeated again. We leave out fold number 3. We train our model using fold 1, fold 2, fold 4, fold 5. After that is done, we then evaluate our model using fold 3. The process goes on and on. So here, we are going to import k-fold from the Scikit-Learn library. We are going to create an empty array for the scores. And then we are going to initialize the k-fold is equal to k-fold. With the number of splits, we need about 10 folds. And then the random state is 42. And then we shuffle, like if you want to shuffle our data set here, but we just say folds. And then we need to loop through all those folds. So to do that, we say for training index in k-fold.split our data set. So we want to loop through all the splitted folds in our data set. We then print out the training index, the test index, and then we initialize our xtrain, xtest, ytest, ytrain, ytest is equals to a x training index, and then the x the test index, y the training index, y the test index. And then we then fit our k nearest neighbor algorithm into the k-fold. And then we then append the scores. We then add the scores to this empty array that we have created here. So if you do that, you'll see that the k-fold is giving us training index as well as the test indexes. And then if we print out the score, you see that the score is 93.9, which is almost 94. And then we print out all the scores. So thanks for watching, guys. I hope this video helped you a lot on cross-validation. So I urge you guys to stay safe and stay at home. Thank you guys for watching. Cheers.
Hello guys, and welcome back to my videos. So in this video series, for applied machine learning, I'm going to be showing you how to use machine learning for real world cases. So in this scenario, we have credit card fraudulent transaction. So we'll be trying to use machine learning to detect fraudulent transaction. So I got this dataset from Kaggle. So this dataset presents transactions that occurred in 2 days, where we have 492 frauds out of 284,807 transactions. So you can see that the dataset is highly unbalanced. The positive class, which is frauds, account for 0.172 of all the transactions. The dataset also only contains numerical input variables, which are a result of principal component analysis transformation. So due to confidentiality issues, we were not given the labels of these features. They were just labeled V1 up to V28, and since they went under principal component analysis. So before principal component analysis is done, so these features have already been scaled by the Kaggle team or the source of the data provider. So our goal in this dataset is to identify fraudulent transaction, and there's other thing that we should note. So in this case, we are dealing with imbalanced datasets. We can see that we have 0.172 of all transactions are frauds. So we can see that the number of non-fraudulent transactions is way too big than the number of fraudulent transactions. So I'm going to show you how to use other techniques such as random undersampling and random oversampling to create a subset of the dataset that contains equal distribution of fraudulent transaction and non-fraudulent transaction. So also note that since our dataset is imbalanced, we do not use the accuracy matrix. So we'll be using the area under the precision recall curve, and then we also the confusion matrix is not meaningful for an imbalanced classification. So the first step we are going to do is we are going to import our dependencies. We are going to import NumPy, which is also used for mathematical operations if you are familiar. We are going to import TensorFlow, which is a library used to create neural networks. And then we are going to import Matplotlib, which is a library that we use for visualizations, as well as Seaborn. We also use it for visualization. And then we are going to import Scikit-Learn libraries. So Scikit-Learn libraries use them for performing principal component analysis, and also they have traditional machine learning algorithms such as logistic regression, the support vector classifier, k-nearest neighbor classifier, decision tree classifier, random forest classifier. So if you are not familiar with any of these algorithms, you can watch any of my previous videos. I've explained how the logistic regression work, the support vector classifier, the k-nearest neighbor, the decision tree, and also the random forest classifier. So we have also other libraries such as the model selection, where we're going to implement the test split that we use to split our dataset into test set and then into training set and test set. And then we are going to import also the pipeline. If you are not familiar with the pipeline, I also recommend that you watch my previous videos on where I explained how to use the Scikit-Learn pipeline. So the next thing is I'm going to load this data, this CSV file that contains our credit card information. So I've stored this file on my disk. So the next thing is I'm going to use pandas, which is a library that we use for pre-processing. So here I'm going to use the data frame df, which I define as df is equals to pd.read csv, and then in that read csv file I'm going to pass in my dataset, and then the df.head is going to print out the first five rows in my dataset.
as you can see, so this, as you can see, I think the computer is still processing. Okay, let's wait. So as you can see, my columns, I have the time. So I have V1 up to V28, and we're also given the time, which is the time in which the transactions occurred, and also we're also given the amount of transactions that were the amount of transaction that were okay, and then we have the class. So the class 0 represent a non-fraudulent transaction, and class 1 represent a fraudulent transaction. So this is what we call a binary classification situation, where one represented a positive outcome, which is fraudulent transaction, and 0 represents a negative outcome, which is a non-fraudulent transaction. Okay, so in the next we are going to have the df.describe, which is going to give us a description of our data set, which is going to give us a description of our data set. As you can see that the minimum amount of transaction, the mean of the transaction, as you can see, this is the mean of the transaction, is $88.34. So as I will visualize the graph, you will see that this data set, in terms of the amount of transaction, is rightly skewed, is skewed to the right. Okay, so the next thing is we are going to see if we have any missing values. So on Kaggle, they say that there are no missing values for this data set. So the df.columns will show us all the number of our columns. So the next thing now is I'm going to print the overall how our data set is. So we are going to show the no frauds, the class. We are going to print the class of the non-fraudulent transaction and the class for the fraudulent transaction. As you can see that non-fraudulent transaction accounts for 99.83 of the data set, and fraudulent transaction accounts for 0.17% of the data set. So if we use this data set as it is, our algorithm will overfit our data set. So every time we use our algorithm, if we want to detect fraudulent transaction, it's always going to give us an outcome that a transaction is non-fraudulent, right? So there should be a scenario. So there should be a solution to this. So a solution to this is to create another subsample of our entire data set that is the equal number of classes. So that is a balanced equal number of classes. So we can also print the visualization of this graph. As you can see, for our positive classes, you can see it's negligible as compared to our non-positive class, right? So in our data set, we saw that they told us that the features V1 up to V28, they went through principal component analysis, right? So before principal component analysis done, they first scaled all the data sets. So the other columns, which is amount in time, those are the only columns that are not scaled. So we need to scale those columns, right? So here we are going to print the distribution of time and distribution of transaction amount. So as you can see, we say that our mean was around 88, which is somewhere here. And as you can see, our data set is skewed to the right, right? It's skewed to the right, or it's positively skewed. So if you're not familiar with skewness, you can check my videos. I have some videos on skewness, right? And if we take the distribution of transaction time, we can see that there's a time where the number of transactions were declining, as you can see here. So we assume that the number of transactions were declining during the night when people are asleep, right? So now the next step is we are going to import from Scikit-Learn the standard scaler and the robot scaler. So the robot scaler, the advantage of using the robot scaler is the robot scaler is less prone to outliers, right? So now we are going to initialize the standard scaler class. Std scaler is equals to std. We create an instance of the standard scaler class,
and then we create the instance of the robot scalar class, and then now we'll create another column in our data set, which we are going to say scaled amount and then scaled time, which we are going to call scaled amount and scaled time. So in those columns we are going to then fit our transformed values or our scaled values. So here df scaled amount is equals to robot scalar dot fit and transform, want to fit and transform the amount column, and then we reshape the values from -1 up to 1, and then here we are going to fit and transform the time column and reshape the values from -1 up to 1. And then since we have done that, we now have scaled values, so we no longer need our previous columns for time and amount. So now we then use the drop function from the pandas library to drop the amount and the time, and then since we now have scaled amount, we do no longer need them, so we drop them. So now we then assign scaled amount. We then assign this variable scaled amount is equal to this, to the column scaled amount. Scaled time is equal to this column scaled time, and then we then drop the scaled amount and then scaled time, and then we then insert 0 for scaled amount and then 1 for scaled time, right? And then we then use df.head to print the first 5 items in our dataset. As you can see here, we now have scaled amount and scaled time, and as you can see, our values are now scaled. So our values are now in the same range. As you can see, all our features are now in the same range, from scaled amount, scaled time v1 up to v28. They are now in the same range. Right. So before we go on to perform random undersampling, right, what we do is we need to split our dataset before we perform random undersampling. Why? So for testing purposes, we don't want to test on our dataset, on a subsample that is created by random undersampling, right? We want to test our algorithm on the original dataset. So what we are doing is, when we are training our algorithm, we are going to train our algorithm using the data on the random undersampling technique, or using the data on the subsample that we will create using random undersampling or oversampling technique, right? But we want to test our algorithm on the original dataset, right? On the original distribution of our dataset. Okay, so now we are going to import from Scikit-Learn.model selection. We are going to implement the train test split, and then from Scikit-Learn.model selection we are going to import the stratified shuffle split, right? So we are going to print the number of non-fraudulent transaction and the number of fraudulent transaction here, and then we are going, since we are only dealing with features, sorry for that. Since on our training features, we want to train our dataset on the features, so we are going, our training set or our features, our features x is equal to df.drop. We need to drop the class which is our label, so we are going to drop the class column, and then for our labels we are going to assign the class column, right? So now we then use the stratified k-fold. So if you don't know what so stratification is a process whereby we rearrange our dataset so that each class so that our dataset is the overall representation of all the classes, right? So in this situation, we want our dataset to have the overall representation of the fraudulent and non-fraudulent transaction. So that's what stratification means. But stratified k-fold, what it does is first rearrange so that we get the overall representation of our dataset, and then it splits our data set into k folds, right? Let's say if we have if k is equals to 5, that means that we have 5 folds. The first thing we do is we train our data set on 4 folds, and then we use the other remaining fold for testing. After that, we then take that fold that we used for testing, and then with other 3 folds, and then we take another one that we used for training, and then we'll be using that for testing. Okay, so here we have stratified k fold. The number of splits is equals to 5, which is saying that we are going to create 5 folds. Random state is equals to none. So if random state is equals to none, then automatically this will use the np.random for shuffling our data set, right? So for train index, test index in our stratified k fold, we then fit and then we then split, and then we then fit the x variable, our features and our labels, and then we then print the train index, test index, and then original x train is equals to x.ilog, and then we fit these train index and then test indexes, right? So we then turn our original x train values into arrays. Since our algorithm will be using arrays, we need to turn them into arrays. So original x train is equals to original x train dot values. Original x test is equals to original x test dot values. So, and then we see if both train and test set label distribution are similarly distributed. So we want them to have the same distribution. So we use train unique label, train counts label, np.unique original y train, and then we return count is equals to true. And then we do the same for our test labels, and then we print the local distributions. As you can see, label distributions, they are all equally distributed, right? Now we then come on to random undersampling. So what we do with random undersampling is, if we take a look at our dataset, we have 492 fraudulent transactions, right? So what we do is we are going to reduce the number of non-fraudulent transactions to 492, and then we first shuffle the non-fraudulent transactions, and then we reduce them so that they become equal to fraudulent transactions, so that we have an equal data set, we have an equal subsample, right? So here we create a sample, df.sample, and then with the fraction is equals to 1, and then fraudulent data frame is equals to df.log df.class. We use the data frame, and then we use the class item, the class column. If our class column is equals to 1, that means that these are fraudulent transactions. But non-fraudulent transaction, and then let's say if the class is equals to 0, then we select from 1 up to 492 rows. So we want them to be equal to the number of fraudulent transactions, right? And then we use a normal distribution data frame. We then concatenate the fraudulent transaction and non-fraudulent transaction. After doing that, we need to shuffle our data frame rows. So we use the new data frame is equals to normal distributed data frame dot sample, and then use the fraction is equals to 1, and then we use the random state to shuffle our data set, and then we use the new data frame dot head, we then use the dot head from pandas, and then as you can see, now we have a subsample with equal number of distribution for both non-fraudulent transaction and fraudulent transaction, right? If we print the distribution, as you can see, it's now 0.5s to 0.5. We can see that we now have the total number of equally distributed classes for fraudulent transactions and non-fraudulent transactions. So guys, this is the end of the video. This is the end of part 1 for using machine learning for detecting fraudulent transactions. So in the next video, we are going to take a look at how our features are correlated, and we are going to take a look at another technique that we use that is called random oversampling, where we increase the the minority class so that it becomes equal to the majority class, right? Thanks for watching, guys. If this video helped you a lot, please click the like button and share the videos with your friends. Thanks for watching, guys. Hello guys, and welcome back to my video series for applied machine learning. Today we'll be continuing with our problem for detecting fraudulent transactions using machine learning. So as you can remember from the previous video, 99% of we're given an imbalanced data set in this problem. So we have 99% of the data consists of non-fraudulent transaction, whereas the percent of the data set is fraudulent transactions. So if you can remember from the previous video, we solved this issue by creating a subsample which is equal number of fraudulent and non-fraudulent transactions. So we use this by using random undersampling technique. So a random undersampling technique is we remove more features from the class. We remove features from the class with more data set than the other, so that the data set becomes equal. So in this video, we are going to interpret the data. We are going to interpret the data that we are given, and we are going to see the correlations between the data in the type of problem which we are going to solve, which is to detect if a transaction is fraudulent or not. So when we want to see the correlation between our data set, we use what we call correlation matrices. So the first correlation matrix that we are going to create is the correlation matrix for the entire data set. That is the data set which contains both fraudulent and non-fraudulent transactions, and which is the data set which is imbalanced. So this is the data set which is imbalanced. So here the correlation, which is df, which is the data frame that we created in the beginning, is dot correlation. This method is the method we are going to use to create our correlation matrix. And then we then use the seaborn library .heatmap. We pass in the variable that we created here. We pass in the cmap, which is coom, and then we pass in other arguments, and then we set the title as imbalanced correlation matrix. And then for this, and then the second correlation matrix is the correlation matrix of our subsample. Our subsample, which we created using random undersampling technique, which is equal number of fraudulent and non-fraudulent transactions, right? So if I run the code, you can see here, because our data set is highly imbalanced, this affects our correlation matrix. As you can see, our correlation matrix is not showing us much information for our data set with imbalanced, for our data frame with imbalanced data set. But if we check at our correlation matrix, but if you can check from our correlation matrix that we created using our subsample data set, which we created from the random undersampling technique, you can see that this gives us much more information. So as you can see from here, from 0 to 0.8, these are positively correlated features. From here 0 to negative 0.8, this shows negatively correlated features. As you can see, V1, we have this blue color. As you can see, it's around here, which shows that V1 is a negatively correlated feature as to our class, as compared to our class, which is fraudulent transaction, which is equal to 1, which is. So as I was saying, the more negative our value, the more negative our value, the more likely that it will be a fraud transaction. And then for positively correlated value, for the more positive our value, the more likely that it will be a fraudulent transaction. So the next thing we are going to look at, box plots. So what are box plots? In statistics, box plots show the distribution in our data set. In box plots, we have the upper part, we have the upper value, 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 which shows us the highest value in our data set. We have the upper quartile, which is 75% of our data set. We have the we have the lower quartile, which is 25% of our data set, and then we have the lowest value, which is the lowest value in our data set. And then the values that are beyond the lowest values are called the outliers, and the values that are above the highest value are called the outliers. And then this part shows us the median. So as you can see, we are going to plot box plots so that they can show us how the distribution of the negatively correlated classes of the negative correlated classes against our class, which is the fraudulent transaction. So as you can see, these are the box plots showing the distribution of our negatively correlated features in our class, which is the fraudulent transaction. So the same goes for positively correlated features. And then our next step, we are going to look at the anomaly detection. As I was talking about, box plots show us the distribution in data, but the most important thing, they show us outliers. So as I was speaking, that outliers, the values that are beyond the highest value in the box plots are called the outliers. The values that are below the lowest point in the box plot are also outliers. So we have to remove outliers. We have one important concept, which is the interquartile range. So we calculate the interquartile range by the difference between the upper quartile range, which is 75 percentile, and the 25 percentile. So our aim is to create a threshold beyond the 75 and the 25 percentile, that in case some instances you may play around with this threshold, but since we don't want to remove all of the outliers, so because we may lose some valuable data that will affect the performance of our algorithms, right? So the in this case we'll be using 1.5, but you can use a higher threshold. But the higher this threshold is, the less outliers would detect, and the lower this threshold is, the more outliers it will detect. So we need sort of like a trade-off. The lower the threshold, the more outliers it will remove. However, we want to focus on extreme outliers. So we want to focus on the values that are beyond the highest value, and the values that are below the lowest value, because we might risk losing information that will cause our models not to perform well. So as you can see, to remove these outliers, the first thing we do is we create a new data frame, which is the V14 feature fraud data frame. Is equals to new data frame. We pass in the column number, which is V14, and then we pass in new data frame class is equal to 1. So we want to select feature values where our class is equal to 1, which is the fraudulent class. Since our main aim is to detect fraudulent transaction, we then convert these values into arrays by using the dot values, and then we create the Q25 value, which is the lower quartile, Q75, which is upper quartile. We then use the numpy library for np.percentile. So np.percentile V14 fraud using our new data frame that we created, and then we pass in the 25 value. So what this piece of code does is that it selects the lower quartile for our data, and then the np.percentile V14 fraud, we pass in the new data frame that we created above, pass in 75, which is the 75% of our database, or of our data set, which is 75% of our data set. And then we print in the 25, the lower quartile, the upper quartile, and then we pass in the variables Q25 and Q75. And then we want to find, as I was saying, the most important concept when you want to remove outliers is the interquartile range. So to calculate the interquartile range for V14 feature is equal to the upper quartile, which is Q75, minus the lower quartile, which is Q25. We then print in the interquartile range. To cut off to cut off the outliers, remember we would multiply the interquartile range by 1.5, and then we have V14 lower, which is so lowest value, V14 upper, which is the upper value. So here V14 lower, we want to remove the outliers that are lower than the lower quartile, which is Q25. We say Q25 minus V14 cutoff. This will show us the lowest value, and then the lowest value in our data set, and then Q75 plus V14 cutoff. This will show us the values that are more than the values that are more than the upper quartile. We print the cutoff V14 lower, V14 up, and then to remove the outliers, we say outliers. We'll create a variable x for x in V14 fraud, which is our data frame that we created at the beginning. If x is lower than V14 lower, that means if x is lower than the lower quartile or the lowest value in our data set, or if x is greater than the upper quartile, or if x is greater than the highest value in our data set, we print feature V14, we print the outliers. So this will print the outliers, and then print V14 outliers. So now this part is where we remove the outliers. So create a new data frame. The new data frame is equals to, we then use the pandas library function, which is the drop. We are going to drop in our new data frame every value that is greater than the V14 up, any value that is greater than our highest value, or any value that is greater than, that is lower than our lowest value. So that's how we remove the outliers. We then print the outliers. The same goes for fit-curve, removing outliers for our feature number fit-curve. We do the same process that I've said above. We create V14 fit-curve fraud, a new data frame fit-curve. We pass in the column number. We select the class which is equals to 1, since we are only more focused on fraudulent transaction. We convert this into array using the dot values, and then the lower quartile, which is Q25, upper quartile Q75, is equal to np dot percentile using the numpy library to perform mathematical function, statistical function. np dot percentile fit-curve. We then pass in the entire data set, which is fit-curve fraud. We want 25% of the data set, which is the lower quartile. We do the same here. We want the 75% of the data set, which is the upper quartile. We calculate the interquartile range, which is the upper quartile minus the lower quartile. V cutoff, which is equal to interquartile range for our fit-curve feature multiplied by our threshold, which is 1.5. But you can change this threshold and you can play around with this threshold. Fit-curve lower, fit-curve upper is equals to the lowest value in our data set is the lower quartile minus fit-curve cutoff. The highest value is the upper quartile plus fit-curve cutoff. We then print these values. We then loop in our data. We first create our variable x, and then loop in for this variable x in fit-curve fraud if x is less than fit-curve lower, or if x is greater than fit-curve upper. We then print in the outliers, printing the fit-curve outliers for fraud cases. Then we then create a new data frame without outliers. In this data frame, that's where we cut off our outliers. New data frame is equals to new data frame dot drop. We drop in all values that are greater than our upper quartile, or all values that are lower than our lower quartile. We then print in this value, as you can see. And then, as you can see, we do the same for feature V14 feature fit-curve, and then we print these box plots again. As you can see, if you print these box plots again, you can see now that we have a few outliers, as we did not remove all outliers, but as you can see now, we don't have as much outliers as before. So thanks for watching, guys. I hope this video helped you understand how we can see how our data is correlated and how we can use box plots to show us the distribution in our data set. So in the next video, stay tuned for the next video. In the next video, we'll talk about principal component analysis and other dimensionality reduction algorithms such as t-SNE. Thanks for watching, guys. Cheers.
To my video. So in this video, we'll be analyzing patient survival after 1 year of treatment. So we'll be using machine learning to predict the survival of patients after their 1 year of treatment, right? So the first thing that I'm going to do is I'm going to import the dependencies. The next thing is I'm going to assign this variable data, and then we are going to read the data using the read CSV function from pandas. And then we are going to display the first 5 items in our data set using the head function. So now the next thing that we are going to do is we want to read all the treated with drugs value counts. This will return all the values in our column treated with drugs here, in our column treated with drugs. So if we analyze our treated with drugs values, we can see that we have some values are in uppercase and some values are in lowercase. So we need to change those values into uppercase. So what we do is select the column treated with drugs is equals to the column treated drugs to convert the string into uppercase using the dot upper. And then if we select again the treated with drugs column, we can see that now all our values are in uppercase. And then we are going to analyze the patient column. So there are 2 ways of doing it to access columns. There's this one where we use the data and then open square brackets, and then we put the name of the column, or we can do it directly by data.patient smoker, which is the column name, dot value counts. This is going to return all the values in our patient smoker. We have no, yes, no, yes, yes, yes. As you can see here, what's happening is that maybe this no is a no without a space. Here the yes, it's a yes without a space. Here it's a no with a space, yes without a space. So as you can see that we only have 3 categories here: no, yes, and cannot say. But somehow we are getting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 categories. So what we need to do is we're going to use a function def smoke, which is going to accept a value r. If r is equals to no, or r is equals to no with spaces, we are going to just return no. Or else if r is equals to yes, or yes with the space, or yes with the double s, or yes with the double s and space, we are going to return yes. Else we are going to return cannot say. So now we are going to say we are going to select our column, and then we are going to apply our smoker we are going to apply our smoker function to convert our values into 3 categories. And then we have data patient rural urban value. So we have patients from rural areas and patients from urban. We can see that we have 17,482 from rural areas and 7,597 from urban areas. And then we have patient mental condition value counts. We have 25,000 who are stable. And then now we are going to perform what we call exploratory data analysis. So exploratory data analysis is a way in which we analyze our features and we analyze our features and get the meaning. What are the features telling us, right? So now we are going to plot a histogram SNS.count plots with our x value survived the first year of treatment, and then our y value or our data is going to be our data set, right?
as you can see that almost 9,000 patients did not survive after the first year of treatment, and then something like 16,000 survived after the first year of treatment, right? So now we'll perform EDA on continuous variables. So continuous variables are variables with numbers, right, that represent numbers. So we are going to say numeric features is equals to data. Our data, remember our data variable, dot select d types. This is a pandas library. Select d types. Data dot select d types include np dot number. So what this is doing is just telling us that we only want numbers, right? And then numeric features dot columns. Now this is going to display features with columns only. We have the ID, patient case, situation, diagnosed condition, patient ID, patient age, patient body mass index. This is the patient mental condition. These ones, they are categories from A to Z, and then number of previous condition, and then we have survived first year. So now what we are going to do is, now that we have, these are our features, but as you know that the ID, patient case, situation, and the patient ID, the patient ID is used to identify a unique patient, and then ID, patient case, situation, I think this is going to identify the situation of each and every patient. So these two are not useful in our machine learning algorithm. So what we are going to do is we are going to say we are going to create another data frame. Numeric data is equals to diagnosed condition, patient age, patient body mass index, number of previous condition, and then survive first year. And then we are going to display the first 5 items, and then you can see now we have our numeric data. And then the next thing that we are going to do is we are going to check for null values. Since we do not want to input data missing values in our machine learning models, because that would disrupt the performance of our machine learning models, and also that will also compromise our prediction. So now we can see that number of previous conditions, we have 1,356 missing values. So what we now do what we can do to fill those missing values, we select the number of previous conditions, data number of previous conditions goes to data number of previous condition. We then fill the number of previous conditions. We then fill the number of previous condition column using the fill NA, which is a library from pandas to fill null values with the mod. So what is the mod? So the mod is the number that appears the mod. So I think you can even use the mean and the median, right? And then we can now say numeric data is equals to data number of previous condition, since now we now have all our values are now filled. So now we now check for null values. As you can see, now we do not have null values. So let's look at basic statistical distribution of our numerical columns. So you can see that we have the count, the mean, which is the average, standard deviation, which shows how our values are spread around the mean. We have the minimum, we have the lower quartile, we have the lower quartile, upper quartile, and then we have the median quartile, and then we have the maximum value. And then observations. As you can see, the minimum and maximum values are values for all numerical columns. The mean and median 50% value of all numerical columns are nearly the same. A good way to visualize the information would be to use box plots. So what are box plots? So box plot is a great way to visualize, to get a visual sense of the entire range of data. It can tell about outliers or what their values are. It can also tell you if your data is symmetrical, how tightly your data is grouped, if and how your data is skewed, right? So in the box plot, we have the minimum value, the first quartile, the median, the third quartile, and then the maximum value. So what we need to do to plot box plot, we are going to drop the survived first year column. Since this survived first year column is not our feature, this is our target variable, so we need to drop it. So we are going to loop through the entire survived first year column, and we drop it. So we say for feature in numerical data that drop survive first year, x is equals to 1 shows that along columns dot columns s, and then we're going to use sns dot box plot survive the first year is our x value, y is our feature, and then data we're going to input our numeric data, and then we are going to use pot.show to visualize our data set. As you can see, diagnose condition, patient age, patient body mass index, and then number of previous condition. So guys, I'm not going to tell you to explain further how we can interpret our data using box plots, but what I'm going to do is I'm going to put links in the description that will help you to understand box plots, right? So data is now dot sum. So now we are going to look at our categorical features. Remember, we are looking at numerical features. What are categorical features? So categorical features are features that represent categories, like yes, is a patient a smoker, yes or no. Those are categorical features. As you can see, the patient mental condition, A condition, we have 1,556 missing values. Same goes for B, C, D, E, up to and Z. So we need to fill those missing values. So what we are going to do is we are going to also treat it with drugs as missing values. So what we are going to do is as 8 missing values treated with the drugs. Data, we are going to select the treated with drugs column is equal to treated with drugs column, fill the missing values with fill NA function, and then we are going to use treated with drugs dot mode. We are going to fill with the number that appears the most. The same we are going to do for patient mental condition categories A, B, C, D, and E, right? So let me just run the kernels. As you can see, now we do not have any missing values. So EDA on categorical data, we are going to perform explanatory data analysis on categorical data. So what we are going to do to select the categorical data is we are going to drop the numerical data from our main data frame, which is from the data variable. So categorical data is equals to data dot drop numerical data dot columns, x is equals to 1. So we are going to drop numerical data columns. So categorical data dot drop patient, we are also going to drop the patient ID, patient case situation, and then if we run, we can see that now we are left with categorical data. Treated with drugs, these are categories for drugs. Patient smoker, no. Patient raw, urban, rural, and then patient condition, right? So the next thing that we are going to do is categorical data dot n unique. As you can see, that treated with drugs has 64 unique values. Patient smoker has 3 unique categories. Patient rural has 2 unique. Patient mental condition has 1. A has 2. So now what we need to do is for feature in patient smoker, patient rural urban, patient mental condition, we are going to plot a histogram with our features. X is our feature, and then we are going to provide the data as survived. The data is survived first year, and then the data is going to be the categorical data. The who is going to be the survived first year. The data is going to be the categorical data, and then what we are going pot.fix size 15.5. This is the size. This is going to be the size. This is going to be the size of each histogram. And then xns.count plot, we are going to our x value is treated with drugs, survive first year, and then data is equals to categorical. Let's see. So as you can see, if a patient is a smoker, for non-smokers, we can see that 10,000 people survived for non-smokers, and then something like 4,000 did not survive for non-smokers. As you can see here, almost 5,000 smokers survived first year of treatment, and almost 5,000 smokers did not survive first year of treatment. If you compare these two, we can see that non-smokers are more likely to survive as compared to smokers. The next thing is patient, rural, urban. We can see that from urban areas, we can see that almost 4,000 survived after first year of treatment, and almost something like 3,800 did not survive after first year of treatment. And then we can see that in rural areas, almost 6,000 did not survive after first year of treatment, and then something like 12,000 survived after first year of treatment. So that shows us that people in rural areas are more likely to survive after first year of treatment. And then we can see that patient mental condition, we can see that stable. People with stable mental conditions are more likely to survive as compared to people who are not stable mentally. So this is the insight that we gain from our features. So then I think I made a mistake somewhere. So the next thing that we are going is pre-processing and data cleaning of categorical variables. Guys, remember, when dealing with machine learning models can only understand numbers. So as they understand numbers, what we need to do is we need to convert our categorical features into dummy variables. So what are dummy variables? For example, if a person is a smoker, if a person is a smoker is represented by yes, we are going to input that by 1. If he's a non-smoker, we are going to input that by 0. So drugs, treated with drugs column, string dot get dummies separated by space, drug dot head. As you can see, now we have converted. So that means the 1 means that this person dx1 was treated with drugs dx1, 0 was not treated with drug dx1, 1 represents presence of dx1, 0 that means that dx2 is not present, 1 represents dx6 is present, 0 means dx6 is not present. So now what we do is we are going to concatenate it into our data. Say data.pd.concat data, and then we are going to concat our drugs variable here with the dummy variables into our main data frame, right? Data is equals to, and then we are going to drop the treated with drugs since this does not contain dummy variables. So now what we get is we now have categorical features for treated with drugs. Patient smoker is also a categorical column. We need to create dummy variables for it too. As you can see, we have yes or no, cannot say. But cannot say, we cannot say it's a category. Since someone says cannot say, we can just classify it as no. So what you do is data.patient column patient smoker. If it's equal to cannot say, then we need to convert it into no. And then the next thing is mental condition, patient mental condition. We are going to drop this patient mental condition since we only have one value, which is stable, so it does not give us any other meaningful insight. And then we get data.get dummies. Get dummies. We want to input dummy variables for patient smoker and rural to urban. As you can see, now we have dummy variables into our data set. So the other two variables I told you about are the ID columns, the ID, patient case, situation, and patient ID. We can think of removing these columns if these are randomly generated value and there is not any ID repeated like we had in the passenger ID. So we are going to change these. We are going to drop these values since they are generated values and they don't give us any meaningful insight. So since they don't give us any meaningful insight, so now what we can do is we can drop the ID, patient care, situation. We can drop the ID patient case situation. Now what we are going to do is prepare our training and test data. So for our X data, we are going to drop the survived first year, since it's not our feature, it's a target variable, and then we are going to assign it to the Y variable, right? The next thing is we are going to split our data set into training and test set using the train test split. X train, X test, Y train, Y test is equal to train test split, X, Y. Want our test size to be 20% of the data set, random state is equal to 1. And then our classifiers, we are going to create a dictionary for our classifiers. So we have our key logistic regression, instance of logistic regression classifier, k nearest neighbor, and then we have the nearest neighbor classifier, key for support vector machine, support vector classifier, decision tree classifier, decision tree classifier, other boost classifier, other boost classifier. So now from Scikit-Learn.module selection, import cross validation score. So this is going to give us validation score for our module. For key, and then our classifier, this is our key classifier. In classifiers.items, this is our classifier.items. We are going to loop through this dictionary, and then we are going to fit each and every classifier to our training and test set. And then training score is equal to cross validation score classifier. We're going to provide this classifier X train, Y train, and then we are going to provide a CV is equal to 5, and then we are going to print our classifiers, classifiers.class, classifier.name, and then we are going to print also the accuracy of our classifier. And then we are going to name X train. I think I did not run this. And then after our modules are done, we are going to plot a confusion matrix for our modules to see how it correctly classified and how it misclassified our data set. And then so now the classifiers are training. So what I'm just going to do is I'm just going to pause the video, and then I'll come back when it's done training. Hello guys, and welcome back. Now that our model has finished training, we can see that the best classifiers are other boost and gradient boosting classifiers. So I selected the other boost and the gradient boosting classifiers, and I used them to plot a confusion matrix. As you can see, these are their confusion matrices here. And then from Scikit-Learn, import classification report to then paste the Y test actual values, and then the predictions of other boost, actual values, predictions of the gradient boosting, precision, recall. So what you can see from what we can see from this is that our recall for other boost, our recall is 90%, our precision is 84, and then our accuracy is 83. So recall is the true positives divided by the total number of actual positives, and then the precision is the total number of true positives divided by the total number of predicted positive, right? So precision, and as you can see, other boost has a precision of 84, and then gradient boosting has a precision of 86. So as you can see that other boost is actually classifying more, is actually performing well as compared to other boost, but the difference is slightly low. So thank you for watching, guys. If you've watched this video, please make sure you share this video with your friends, and also you can also, as a homework, you can also try to implement neural networks, or try to implement other machine learning algorithms. Thanks for watching, guys. Cheers.
Hello guys, and welcome back to my YouTube channel. So in this video we are going to be predicting loan eligibility of a customer using machine learning. So the first thing that we are going to take is we are going to import our dependencies, and then we are going to load our loan prediction dataset from memory. using the pandas library. So if you have not yet watched my pandas series, I urge you to go back and watch my pandas series so that you do not get lost as we go along the video. So to read our loan prediction data set, we are going to use data frame df is equals to pd.res.csv, and then we are going to provide the path that contains the CSV. So the next thing that we are going to do is we are going to check the shape of our data set using the dot shape object, which is a 614 by 30. And then the next thing that we are going to do is we are going to display the first 5 items in our data set. The first 5 items in our data set, as you can see, we have the loan ID, we have the gender, we have if a person is married, dependents, education, if the person is self-employed, their income, the co-applicant income, loan amount, term, credit, and then property area, and then also the loan status, right? So this is an example of a binary classification problem. So we are going to get the info from our data set. We can see that from loan ID we have 614 none now object, and then also we have married from married we have 611. So this displays each the number of items in each column, right? And then we are going to use the dot describe. The dot describe is going to give us the count, the mean, standard deviation. And then what we are going to do is we are going to set the credit history. As you can see, credit history. Credit history. We are going to set the data type of this credit history as an object. So to do that, we are going to select the column TF credit history. Is equals to credit history as type of object, and then we are now going to include as a categorical data. df.describe include O, which is an object. So now, as you can see, we have now included it. So the next thing that we are going to do is we are going to drop the loan ID. So in this case, the loan ID is not useful. The loan ID is only used by banks maybe to identify the applicant form. It's a way of identifying maybe the applicant's form, give it a numbering system, right? So we are just going to drop it from our data set. And then we are going to check if there are any duplicated values. As you can see, we don't have any duplicated values in our columns or in our entire data frame. Now, what we are going to do is we are going to look at the distribution of our data set, right? As we look into the distribution of our data set, we can see that our data set is an imbalanced data set. As you can see, more people were given loans than people that were not given loans. As you can see, Y stands for yes, about 420 or more people were given loans, and then here it's about 200 people were not given loans. And then we are going to use the dot columns object to show the columns in our data set. As you can see, we have the gender, we have married, dependents, education, self-employed, applicant income, co-applicant income, loan amount, term, credit history, property area, and loan status. And then we are going to display the first item in our data set, as you can see now. So now the next step that we are going to do is we are going to compare our features in our data set with the loan status, right? So the first thing that we are going to do is we are going to create the facet grid using Seaborn, which is a visualization library that works on top of Matplotlib, right? And then we provide the data set. The column that you want to plot a facet grid is the loan status. We use the loan status, right? If it's yes or no. And then we provide the size, which is 3.2, and then the aspect ratio, which is 1.6. The next thing that we are going to do is we are going to compare our loan status with the credit history. As you can see, we say grid.map. We are going to map through the credit history, right? So if I run through, you can see that people with a credit history of 1 were more likely to be given a loan, right? than people with a credit history of 0. As you can see that we can see there are about 5 people or 10 people that were given a loan with a credit history of 0. And then the next thing that we are going to see is that some people with a credit history of 1 were not given a loan, and some people with a credit history of 0 were not also given a loan, right? And then the next thing that we are going to do again, we are going to compare the gender, right? We want to see the gender. So we are going to plot the facet grid for the loan status, and then we are going to use grid.map to look through the gender. So as you can see, more males are more likely to be given a loan than females, right? As you can see here, the graph for the bar chart for males is greater than for females. As you can see also, males are more likely to be declined for a loan than females, right? So the next thing that we are going to check is we are going to compare our loan status with our merit feature, right? So now we are going to use what we call a count plot, right? So if you have not watched, if you are confused about what is a count plot, I urge you to watch my Seaborn tutorial, my introduction to Seaborn tutorial. So it will just pop up on the screen. You can click there and go and watch and come back and watch this video. So we are going to plot a figure of fixed size of 15 by 5. And then we are going to use sns.countplot to then provide the x variable, which is merit. And then we are going to use the loan status as who, and then we are going to provide the data as our data frame, right? So as you can see, from our data set, right? As you can see from our data set that people, who are married are most likely to get a loan than people who are not married. As you can see from this, we can see that this graph, people who are married are more likely to get a loan than people who are not married, right? And also, we can also see that the other thing that we can see that people who are married are most likely not to get a loan as compared to people. People who are married are more likely not to get a loan than people who are not married. As you can see, if you compare this with this one, right? And then the other thing that we are going to look through it is the dependence, right? So we are going to use a count plot, and then we provide the x variables dependence compared against the loan status, and then we provide our data frame, right? As you can see, people with 0 dependence, right? People with 0 dependence are more likely to get a loan. People with 0 dependence are more likely to get a loan than those with dependence. As you can see, this one is 1 dependent, and then this one 2 dependents and 3 dependent. And we can also compare this. People with no dependence are more likely also not to get a loan, as you can see with this no, and you compare it to the others, right? And then the next thing that we are going to compare is the level of education, right? If the person is educated, right? So we are going to also use a facet grid, right? So we're going to say grid is equals to sns.facet grid. We are going to provide the data frame. Our column, we are going to use the loan status. The size is going to be a 3 by 2, and then the aspect ratio is going to be a 1 by 6. And then we are going to use the grid.map to map through the sns.countplot, and then we are going to provide the education variable, right? So as you can see, a graduate is more likely to get a loan than a person. A graduate is more likely to get a loan than a person who is not graduated. At the same time, a graduate is more likely to be declined a loan than a person who is not a graduate, right? And then the next feature that we are going to look at is the self-employed, right? If the person is self-employed. So we are going to use the facet grid again. We'll provide the loan status, and then we are going to look through using the grid.map sns.countplot self-employed, right? If the person is self-employed. So we can see that if a person is self-employed, they are more likely not to get a loan. As you can see, if they are self-employed here, they are more likely not to get a loan And then also you can see that they are more likely to be declined if they are self-employed, right? And then the next thing that we are going to look at is the property area, right? So we are going to use the count plot, SNS.count plot to provide the property area. We are going to provide the loan status. We are going to compare it against loan status. Our data is going to, we are going to provide our entire data frame, right? As you can see from this, a person from a semi-urban area, they are more likely to get a loan. And then a person from urban areas, again, they are more likely to get a loan. And then a person from a rural area are less likely to get a loan. As you can see, their bar graph is less than any of these two. And you can also see that a person from urban areas and rural areas are more likely to be declined of a loan as compared to a person from the semi-urban areas. So the next thing that we are going to do, we are going to plot a scatter plot of the applicant income and the loan status, right? As you can see, most people that are given loans, their income is more likely to be between 0 and 20,000. As you can see, that's where there is dense. That's where this this blue is dense as compared to others. And also, you can also see people from 0 to 20 are also likely to be declined a loan, right? So now, what we are going to do is we are going to look at the numerical data, right? So we are going to use the loan status dot median, and you can see that the applicant income, the median is 338,000. And then the other thing that we are going to do is we are going to sort the values, right? We are going to sort the values using df dot sum dot is now. We are going to check if the values is now, and then we are not going to sort them. As you can see, we have now values on credit history. We have 50 now values on credit history, 32 on self-employed, 22 on loan amount, 15 on dependence, 14 on loan amount term. So now the thing that we are going to do is we are going to separate our values into numerical and categorical values. So categorical values are features that show categories, and numerical values are features with numbers. So we are going to say K data is equals to an empty array, num data is equals to an empty area. So we are going to look through for I, C in enumerate. We are going to look through the df d types, which stands for which for looks for the data types in our data frame. If C is equals to an object, if C is equals to an object, we are going to append it to our empty array as categorical data. Else we have numerical data, right? And then what we are going to do is after next, we are going to just transport the categorical data and the numerical data. And let's look at the categorical data. As you can see, we have gender, married, dependence, education, self-employed, credit history, urban, and loan status. And then we are going to look also at the num data with applicants, numerical data with the applicant income, co-applicant income, loan amount term, right? So the next thing that now we are going to do is we are going to say the categorical data is equal to categorical data dot. We are going to use a lambda function to fill in the missing values, right? So we are going to use the lambda function to check if there are any to fill in the missing values, right? And then after that, we are going to check if there are any missing values. As you can see, we don't have any missing values. And then now we are going to our numerical data dot fill, and a method is called, we are going to use bfill, and then in place is equal to true. And then we are going to check if there are any missing data, and you can see we don't have any missing data. The next thing that we are going to do, we are going to use the label encoder, right, to change our categorical features into one word values, right? So the thing is, machine learning algorithms do not understand text, they understand numbers. So if a person is a graduate and not graduate, what we are going to do is that for education, if a person is a graduate, we are going to place 1. If he's not a graduate, we are going to place 0, right? So let's do that. And then let's then transform the target column. Now for the target column, we know that y is equals to 0. Y is equals to 0. That means that if it's yes, we are going to place 0. If it's no, we are going to place 1. And then, okay, let's do it the opposite. If it's yes, we are going to place 1. If it's no, we are going to use 0, right? And then the target, our target is equals to categorical data and then the loan status, right? We are going to use the loan status as our target variable, as our target feature, right? And then the categorical, we are going in the categorical data frame, we are going to drop the loan status since it is now our target value, right? So now we are going to also transform other values in our data set into one word encoding. And then let's see, as we can see now, if a gender male, maybe it's male, we are going to place it 1. If a person is not married, it's going to be 0. If he's married, it's going to be 1. And then the next thing that we are going to do is we are going to concatenate our categorical features and our numerical features into a single data frame. Since we have transformed both of them, as you can see, now we have both of them. So the next thing that we are going to do, we are going to train our model. So to train our model, what we are going to do is we are going to say our x variable is going to be pd.concat, the categorical data, numerical data, and then along columns. And then our y is going to be the target. So remember, I said the target, we already used the target, right? And then the other thing that we are going to use, we are going to use stratified shuttle split to train our model. So if you are not familiar with the stratified shuttle split, I urge you to watch my video on stratified shuttle split. And then the other thing is we are going to initialize our models. We have logistic regression, k-nearest neighbor, the support vector classifier, decision tree classifier. We're going to create a dictionary of our models. And then the key for logistic regression, and then the value is the logistic regression object. The same goes for k-nearest neighbor. And then the other thing that we are going to do is we are going also need to calculate the precision, recall F1, loss, accuracy, right? And then what we are going to do now is going to train our train and evaluate our model. For name model in models.items, right? We have this. We are going to loop through the models.items. We are going to print the name of the model. We are going to fit it to our training and test set, going to calculate the loss, and then we are going to finally evaluate the model. And as you can see, we have the logistic regression with a precision of 0.782, 0.797, 0.870. And then we also have k nearest neighbor support vector classifier and the decision tree classifier. So thank you for watching, guys. The first part of our predicting our loan eligibility using machine learning. In the next video, I'm going to be talking about the precision recall F1 score, and we are going to look at how we can improve our model training. Thanks for watching, guys. Cheers. I did not want this video to be long.